When that moment comes, the balance shatters. Scuti is losing mass. Its outer layers drift away, carried off by stellar winds. Streams of particles blown by radiation pressure. Over time, this process peels the star apart. It's one of the reasons astronomers debate its actual size. Because the outer envelope is so diffuse, it's hard to say where the star truly ends. You reflect for a moment on how little of this was known just decades ago. In the 20th century, red supergiants were assumed to be rare, mysterious anomalies. Only with the rise of space telescopes and precise spectroscopic methods did we begin to map their true dimensions. And even now, some data is debated. Distance estimates, mass loss rates, temperature fluctuations. But uncertainty doesn't dim the wonder, it expands it. Some researchers propose that UY Scuti may shrink as it evolves, its mass loss and internal changes gradually collapsing it into a hotter, smaller star before the final supernova. Others believe it may be on the brink already, that its next contraction could be the last. The supernova of a star like this would not just be bright, it would be transformative, a release of energy so vast it could outshine an entire galaxy for weeks. Neutrinos would flood space. Elements like gold, platinum, and uranium would be born in that furnace. This is cosmic alchemy, stars turning themselves inside out, to seed the universe with complexity. But tonight, that moment is not here yet. Tonight you float beside a star so large, your mind falters at the scale. The texture of it, the slowness of its surface, the quiet distance of its core. You feel as though you are orbiting a...
वेटर यार भाई मुर्शिद प्यास लग रही है यार
मुझे भी
बोलो डब्बे में क्या है
गाड़ी
सोना नहीं
बोलो भाई
अरे नहीं भाई भाई यहाँ से सारे मिलके बोलो ओके
अरे ये नहीं खोलना
50 रुपए इसमें क्या मिलेगा
अरे 50 रुपए में अब मिले प्यास बुझाने की सुपर पावर
नई 3-in-1 रिवाइव विद इलेक्ट्रोलाइट्स विटामिन्स एंड ग्रेट टेस्ट प्यास बुझाए पूरी तरह
मजा आ गया
अबे इसमें तो सच में सुपर पावर्स हैं
वो भी सिर्फ 50 रुपए में
नई रिवाइव
Even larger, its name is whispered among catalogs and in quiet debates. Stevenson 218. You turn toward it, letting the light of UY Scuti fade gently behind you, and begin the slow glide, deeper into the realm of hypergiants. You learn why some stars are larger, others heavier, and how this affects their fate. As you drift onward, the red glow of UY Scuti dissolves behind you, like a sunset slipping below the edge of time. Ahead, space stretches wide and cool, a canvas of subtle light and gravitational tension. You move through stillness, but the physics beneath that stillness hums with complexity. Out here, size is not always what it seems. One star might swell to the edge of Saturn's orbit, yet possess only a fraction of the mass of another, smaller, hotter star. In astronomy, the distinction between volume and mass becomes crucial. You let your thoughts wander through this quiet paradox. UY Scuti, for example, is enormous in size, its radius vast, but its mass is relatively modest among giants, somewhere between 7 and 10 times that of our Sun. Compare that to a star like R136A1, which you will soon meet. That one is far smaller in diameter, but could contain nearly 200 or even 300 solar masses. It blazes with intensity, not through sheer size, but by its unimaginable density and fusion rate. Why is that? You consider the balance at the heart of every star, the push and pull of gravity and pressure. A massive star's gravity pulls everything inward, while fusion at the core pushes outward, releasing radiation. This balance defines the star's shape, size, temperature, and lifespan. The more massive a star is, the greater the pressure at its core. To maintain equilibrium, it must fuse elements more rapidly. That intense activity makes it brighter, but it also shortens its life. A giant like R136A1 might burn through its fuel in just a few million years. Meanwhile, a smaller star can shine calmly for tens or even hundreds of billions. Yet not all massive stars are large in radius. Many, like blue giants and Wolf-Rayet stars, are compact and hot. Their outer layers are stripped or compressed. Some, despite burning brightly, are barely 10 times larger than our sun by radius. Nothing like the sprawling atmosphere of a red hypergiant. It's like comparing a bonfire to a smoldering ember the size of a mountain. Both burn, both glow, but one is intense, short-lived, the other diffuse and slow. This tension shapes every step of a star's life. Mass is also destiny. A star's mass determines what it becomes when it dies. If it begins with under 8 solar masses, it might swell into a red giant, and then settle quietly as a white dwarf, cooling slowly, over trillions of years. But if it starts with over 20 or 30 or more, its end is cataclysmic. A supernova, a neutron star, a black hole. There are thresholds, and you pass them silently as you drift. Somewhere behind you lies the boundary between stars that end quietly and those that collapse with violence. Somewhere ahead lies the limit where even neutron stars can't survive their own mass, and space folds inward. Some scientists propose more exotic ends. Quark stars, for instance. Hypothetical objects denser than neutron stars, but not quite black holes. In these stars, neutrons are squeezed so tightly that their constituent quarks may separate, forming a sea of strange matter. No such object has been confirmed yet, but the physics doesn't rule them out. Somewhere in the deep silence, perhaps one already exists. Back in your current path, mass continues to guide the stars you approach. The next behemoth, Stephenson 218, is an oddity. If estimates hold true, its volume exceeds even UY Scutis, and yet its mass, while substantial, is likely under 40 solar masses. It is wide, but not wildly heavy. A reminder that size does not equal strength. This behemoth likely belongs to a stellar association, a loose group of red supergiants known as Stephenson 2, or ST2, located around 19,000 light-years from Earth. The entire region glows in infrared, partially hidden behind a thick layer of interstellar dust. To see it, astronomers peer through long wavelengths, watching for thermal traces that shine. Like heat seen through fog, you reflect on how much of the universe is invisible, not because it's hidden maliciously, but because your human eyes are tuned to such a narrow band of light. Like listening to a song and hearing only one instrument. Fortunately, your thoughts have no such limits here. You float through X-ray bursts and infrared ribbons, through gravity waves and magnetic storms. Each layer of the universe adds another brushstroke to the vast, silent portrait. And as the shape of Stephenson 218 rises before you, still distant, still only a ghostly glow in the haze, you consider the quiet truth that space teaches best. That scale is not always power, that the universe is not arranged by what impresses the eye, but by what holds its balance. You drift slower now, as if nearing the edge of something sacred. You've learned how stars wear their size and mass like masks, some bright and dense, some vast and fading, and ahead, the deepest mask yet awaits. You approach a veiled red hypergiant, cloaked in interstellar dust, barely visible yet vast beyond measure. You pass through the last of the open void, entering a field of mottled shadows. The light here is soft, not because it isn't present, but because it is scattered and filtered by fine grains of interstellar dust. This is the domain of Stephenson 218, a red hypergiant so immense, it defies simple comparison. Its true nature is shrouded, not only in distance but in uncertainty. Even today, it exists in our data more as a probability than a fully resolved object. The veil around it is literal, thick with carbon-rich dust and cool gas, and figurative, in the sense that many of its measurements are inferred from indirect observations. Still, the picture that emerges is staggering. The star lies approximately 19,500 light-years from Earth, in the constellation Scutum, nestled within a massive cluster known as Stephenson 2, a cradle of red supergiants. But Stephenson 218 is not simply one of many. It may be the largest of all, with a radius potentially exceeding 2,100 times that of our Sun. To put that in perspective, if you replaced the Sun with Stephenson 218, its photosphere would reach well past Saturn and possibly graze the orbit of Uranus. You float slowly towards this diffuse colossus, and even now, you can't clearly define its surface. It is more atmosphere than object, more presence than point. Its outer layers are extremely tenuous, more like a fog than a skin. They drift, ripple, and escape into space. The density is so low, you could pass through the outer half of the star without ever feeling resistance, without even sensing that you were inside something at all. And yet, you drift through its outer envelope, immersed in a slow, churning sea of heated gas. Here, temperatures are relatively cool, around 3,000 Kelvin, and the pressure is low, but deeper in the story changes. The further you go, the more intense the heat, the more violent the motion. Turbulence rises, the fusion furnace stirs. Stephenson 218 is thought to be near the end of its life. Like UI Scuti, it has exhausted the hydrogen in its core and is fusing heavier elements in successive shells. Each fusion layer is like a nesting doll. Hydrogen, helium, carbon, oxygen, each deeper, hotter, and shorter-lived. Eventually, as with all massive stars, it will build up an iron core, and when that happens, gravity will win. In a fraction of a second, the balance will collapse, the core will implode, and the outer layers will rebound in a supernova, an explosion that will send shockwaves through the surrounding dust and gas, igniting new stars in its wake. It is the ultimate punctuation mark to a stellar life, but sometimes something even more exotic occurs. If the collapsing core is massive enough, the pressure can go beyond neutron degeneracy, the point where even neutrons resist compression. Gravity wins entirely, space folds in on itself, and the result is a black hole, an object so dense, not even light can escape. It is the final victory of gravity, the quietest and most complete. You float away from this imagined core, back toward the outer layers. Here the gases are lighter, more diffuse. Solar winds blow steadily outward. In massive stars, these winds are intense, stripping away mass at phenomenal rates. Over millions of years, a star might lose half its mass or more before it ever explodes. In lower mass stars like our Sun, fusion will never reach iron. It will stop at helium and carbon, eventually ejecting the outer layers in a soft, glowing cloud, a planetary nebula, and leaving behind a white dwarf, a dense cinder slowly cooling in space. The diversity of stellar fates all stems from this balance, how long fusion holds gravity at bay. And yet, you realize, no star lasts forever. Fusion is a delay, not a solution, a beautiful pause in the collapse that shapes all matter. And without it, there would be no light, no warmth, no planets, no life. In this moment, you feel the deep humility of that truth. Everything you are, all your atoms, all your breath, was once held inside a star's fusion engine, cooked, balanced, released, and given to the galaxy. Somewhere, a new star is forming. Somewhere else, another is fading. And
मेरा नाम लियाकत अली है। यांगो के साथ मुझे 2 साल हो गए काम करते। बोनस 1000 रुपए डेली हमने रखना होता है। फैमिली वाला बंदा ही मेहनत करता है, तो जिम्मेदारी निभाने के लिए ये बहुत अच्छा प्लेटफॉर्म है। सब रियल है, महान अल्लाह से ऊपर अपने करें।
Low rhythm of drifting carry you into deep, unbroken sleep. Good night, traveler. Sleep well. Sleep wide. A star that's died, yet its power makes the universe tremble. Neutron stars, where matter is crushed to the extreme and the impossible becomes reality. Imagine staring into a cosmic void where a faint rhythmic pulse of light flickers like a heartbeat from an unseen star. What could forge such a relentless, radiant pulse, defying the silence of space? Welcome to the enigma of neutron stars, the pulsing hearts of the cosmos, where the ashes of colossal stars beat with a ferocity that reshapes our understanding of reality. These celestial relics born from cataclysmic explosions pack the mass of our sun into a sphere no wider than a city, spinning with a rhythm that echoes across light years. Far beyond what school textbooks taught, neutron stars challenge our grasp of physics, time, and existence itself, inviting us to peer into a universe both alien and awe-inspiring. Neutron stars are not just astronomical curiosities. They are cosmic laboratories where the laws of nature are stretched to their limits. Picture the heart of a supernova, where a dying star collapses, crushing its core into a dense, spinning orb that pulses with energy. This is no ordinary star, but a neutron star, a celestial marvel with a density so extreme that a single teaspoon of its material would weigh as much as Mount Everest. Its surface, smoother than glass, hides a core where matter may dissolve into strange, exotic forms. These stars don't merely shine. They broadcast their presence through beams of radiation, like a lighthouse sweeping the cosmos detected here on Earth as rhythmic pulses. Why do these pulses captivate us? Because they whisper secrets of the universe's most extreme conditions, encoded in a heartbeat that has traveled millions of years to reach our telescopes. This journey into neutron stars is a voyage through time and thought, one that will unravel mysteries school never touched. We'll begin by tracing the historical quest to understand these cosmic hearts, from ancient stargazers who glimpsed their explosive births to the scientists who decoded their rhythmic signals. Then we'll dive into the science of their extraordinary nature, how their immense gravity warps time, how their magnetic fields rival 1 trillion refrigerator magnets, and how they forge the gold in your jewelry. We'll explore modern discoveries from waves rippling through space-time to theories of alien matter lurking in their cores. Finally, we'll reflect on what these pulsing hearts reveal about our place in the vast interconnected cosmos. The neutron star's heartbeat is more than a signal. It's a mirror reflecting the universe's deepest truths. But why should we care about a star so distant, so strange? Neutron stars are not just relics. They are keys to unlocking questions that haunt us. How do stars die, and what do their deaths create? Can matter exist in forms we can't imagine? Might these cosmic hearts hold clues to the universe's origin, or its ultimate fate? As we stand on Earth, gazing at their faint pulses, we're not just observing. We're connecting with a force that shapes reality itself. The neutron star's pulse is a call to wonder, a reminder that the universe is alive with mysteries waiting to be explored. So let's follow this heartbeat, this radiant rhythm, and discover what lies beyond the lessons of school, deep within the pulsing heart of the cosmos. Long before telescopes pierced the heavens, ancient stargazers stood beneath a glittering sky, their eyes catching fleeting bursts of light from distant cataclysms. Could they have imagined that these fiery spectacles were the birth cries of neutron stars, the pulsing hearts of the cosmos? Thousands of years ago, in 1054, Chinese astronomers recorded a guest star blazing in the constellation Taurus, so bright it shone in daylight for weeks. Unknown to them, this was the Crab Nebula's supernova, a stellar explosion forging a neutron star whose heartbeat we still detect today. This cosmic pulse, a rhythm of radiant energy, has echoed through history, guiding curious minds to unravel a mystery schoolbooks barely touched. Let's journey through time, tracing how humanity first heard the universe's pulse and began to understand its profound significance. In the 18th century, as astronomers mapped the stars, an English cleric named John Michel pondered a radical idea. What if a star's gravity was so immense that even light couldn't escape? His dark stars were a faint whisper of neutron stars too strange for his era to grasp. Fast forward to the 1930s, when Fritz Zwicky and Walter Bade, gazing at the cosmos, proposed that supernovae left behind dense cores. They called these neutron stars imagining a stellar corpse, where matter was crushed into a near-infinite density. Their vision was like tuning a radio to catch the faint pulse of a cosmic heart, a signal too weak for the technology of their time. Yet their bold hypothesis set the stage for a discovery that would shake the foundations of astronomy. In 1967, a young graduate student, Jocelyn Bell Burnell, sat hunched over a radio telescope in Cambridge, England, sifting through reams of data. Amid the static, she noticed a peculiar regular blip every 1.33 seconds, as precise as a metronome. At first, her team dubbed it LGM-1, half joking that it might be a signal from little green men. But this was no alien broadcast. It was the pulse of a neutron star, a pulsar spinning furiously and beaming radio waves like a cosmic lighthouse. Bell Burnell's discovery was a triumph, revealing the neutron star's heartbeat to the world. The Crab pulsar, that ancient guest star of 1054, was among the first confirmed its rapid pulse, a testament to a star's violent end. Her work, though initially overlooked for a Nobel Prize, ignited a new era of cosmic exploration. These historical milestones, from ancient skywatchers to Bell Burnell's breakthrough, are like reflections in the cosmic mirror, each catching a glimpse of the neutron star's pulsing heart. They show humanity's relentless drive to decode the universe's signals, even when the tools were crude or the ideas outlandish. Michel's dark stars, Zwicky's dense cores, and Bell Burnell's blips were steps toward understanding a celestial enigma. Neutron stars, with their relentless rhythms, weren't just theoretical curiosities. They were real, their pulses a drumbeat echoing across the cosmos. As we move forward, we'll delve into the science behind these extraordinary objects, exploring how their heartbeat shapes the universe and what secrets it holds for us today. Picture a city-sized sphere spinning hundreds of times per second, its surface pulsing like the relentless beat of a cosmic heart. How can a neutron star, this pulsing heart of the cosmos, defy our everyday understanding of matter and time? These stellar remnants are not just dead stars. They are extreme laboratories where gravity, magnetism, and quantum forces collide in ways schoolbooks never dared to explore. Born from the fiery collapse of massive stars, neutron stars pack the sun's mass into a ball just 20 kilometers wide, creating densities so immense that a single sugar cube of their material would outweigh Earth's entire population. Let's unravel the science behind their extraordinary nature, from their crushing gravity to their role as cosmic alchemists forging the universe's heaviest elements. Imagine squeezing an ocean liner into a thimble that's the density of a neutron star. Its core, crushed by unimaginable pressure, may transform into exotic matter, perhaps a soup of quarks, unbound from normal atoms. This density warps space-time, bending light and slowing time itself. If you stood on a neutron star's surface, an impossible feat, your watch would tick slower than on Earth, a quirk of Einstein's relativity called time dilation. A minute there might feel like hours to a distant observer, as if the cosmic heart's pulse stretches the fabric of reality. This gravity is so fierce that mountains on a neutron star's surface, smoother than a billiard ball, are mere millimeters tall, flattened by the star's own weight. Yet this compact orb spins with dizzying speed, some pulsars whirling 700 times per second, faster than a kitchen blender, sending beams of radiation sweeping across space like a lighthouse's glow. These beams are powered by magnetic fields 1 trillion times stronger than Earth's fields, so intense they could rip apart a spaceship. When a neutron star's magnetic poles misalign with its spin, it emits radio waves, X-rays or gamma rays creating the pulses Jocelyn Bell Burnell detected. These pulsars are cosmic clocks, their beats so precise they rival atomic clocks, allowing astronomers to map the galaxy or test relativity. But neutron stars do more than pulse. They forge elements like gold and silver. During a supernova, rapid neutron capture creates heavy elements, and when two neutron stars collide, as seen in 2017's gravitational wave event, they spew these treasures into space. Picture the cosmic heart pumping, not blood, but the raw materials of planets and jewelry, a celestial forge shaping the universe's wealth. Beneath their surface, neutron stars hide mysteries. Their cores may host strange states of matter, like quark-gluon plasma, where protons and neutrons dissolve. Some theories suggest superfluids flow without friction, creating a frictionless dance within the star's heart. These conditions push physics to its limits.
My work is easy because I use ClickUp. Here's how I get perfect notes from every meeting. I click this toggle to send my AI note taker to my meetings, even if I can't attend. My AI note taker records the entire meeting and creates a full transcript. After the meeting, I get a doc with the recording, takeaways, and even the action items. AI turns these action items into tasks so we actually get things done. ClickUp makes work easy, from personal projects to running a multi-billion-dollar company. Click the link below to create your workspace for free.
Whisper to us today as its radiant beats ripple through modern telescopes. Neutron stars, those city-sized relics of stellar explosions, are no longer just distant curiosities. They're cosmic beacons, illuminating the universe's deepest mysteries. In recent years, astronomers have caught their pulses in unprecedented detail, from gravitational waves born of their collisions to strange matter lurking in their cores. These discoveries, far beyond schoolroom lessons, reveal neutron stars as keys to understanding matter spacetime and even our technological future. Let's explore how the relentless heartbeat of these stars echoes through cutting-edge science, reshaping our view of the cosmos and sparking questions about what lies ahead. In 2017, a cosmic symphony reached Earth, detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO. Two neutron stars locked in a death spiral collided 130 million light-years away, sending ripples through space-time. This event, named GW170817, was a milestone confirming that neutron star mergers forge heavy elements like gold and uranium as their pulsing hearts pump out a cosmic furnace. Telescopes caught the afterglow, a dazzling burst of light, proving these collisions light up the universe. Unlike black holes, neutron stars leave visible scars, their radiant pulses offering a window into gravity's extreme dance. This discovery linked the cosmic heart's beat to the creation of the very atoms in our world, suggesting that the jewelry on your finger owes its existence to such cataclysmic embraces. But what lies within a neutron star's core? Modern theories propose exotic states of matter, like quark-gluon plasma, where protons and neutrons dissolve into a primordial soup. Imagine the cosmic heart compressing matter so fiercely that it mimics the universe's state just after the Big Bang. Experiments like those at CERN's Large Hadron Collider aim to replicate these conditions, but neutron stars are natural laboratories, their pulses encoding clues about physics beyond our reach. Some suggest superfluids swirl in their cores, flowing without friction, while others hypothesize strange quark matter, a stable state denser than nuclear matter. These ideas push quantum mechanics to its limits, with each pulse of the cosmic heart offering a testbed for theories that could rewrite our understanding of reality. Neutron stars also inspire technological dreams. Their precise pulses, rivaling atomic clocks, could guide interstellar navigation, acting as cosmic lighthouses for future spacecraft. Magnetar's neutron stars with ultra-strong magnetic fields hint at energy sources dwarfing nuclear power, sparking ideas for harnessing their radiant energy. Philosophically, neutron stars challenge us if their cores hold alien matter. What does this mean for our place in the cosmos? Are we like their pulses, fleeting signals in an infinite universe? Imagine yourself drifting silently in the vastness of space. Before you, a galaxy spins a luminous whirlpool of billions of stars, gas and dust. The core glows brilliantly, surrounded by spiraling arms stretching out like cosmic ribbons. It's a mesmerizing dance of light and motion held together by a gravitational force so immense it defies comprehension. Yet hidden within this stunning spectacle is an enigma. The visible elements of the galaxy, stars, planets, and nebulae account for only a fraction of the mass needed to sustain this intricate ballet. What is holding these celestial bodies together? What invisible force anchors the galaxy's swirling arms, ensuring it doesn't fly apart? This is the mystery of dark matter, the unseen framework of the universe. It doesn't emit light or energy, making it undetectable by traditional telescopes. Yet its gravitational pull shapes galaxies, clusters, and the universe itself. It is the scaffolding upon which the cosmos is built. The idea of dark matter arose when astronomers noticed discrepancies between what they could see and the behavior of galaxies. In the 1930s, Fritz Zwicky, a Swiss astrophysicist, observed that galaxies in the Coma cluster were moving faster than expected. By applying Newtonian physics, he calculated that visible matter alone couldn't generate enough gravity to hold the cluster together. There had to be some missing mass providing the necessary gravitational glue. Decades later, Vera Rubin and Kent Ford confirmed this phenomenon within individual galaxies. Studying the rotation curves of spiral galaxies, they discovered something astonishing. Stars on the outer edges of galaxies were moving just as fast as those near the center. According to the laws of gravity, this was impossible unless there was an unseen mass extending far beyond the visible boundaries. This realization that most of the universe's mass is invisible reshaped our understanding of the cosmos. Today, scientists estimate that dark matter constitutes roughly 27% of the universe, dwarfing the mere 5% made up of ordinary matter. The rest, even more mysterious, is dark energy. The invisibility of dark matter sets the stage for one of science's greatest pursuits. It's a riddle that challenges the boundaries of our knowledge, compelling us to peer deeper into the fabric of reality. What is this unseen force? How does it interact with the visible universe? And what does its existence mean for our understanding of life? Existence and everything in between. The hunt for dark matter isn't just about solving an abstract puzzle. It's about uncovering the fundamental truths of the universe. If we can understand this invisible force, we might unlock secrets about how galaxies form, why the universe expands as it does, and perhaps even glimpse the forces that shaped the cosmos in its infancy. This is the unseen force shaping our universe. It surrounds us, permeates us, and holds the cosmos together. To understand dark matter is to understand the universe itself. And so the quest begins with questions as vast and profound as the galaxies swirling in the night sky. To uncover the presence of something unseen, scientists rely on the subtle traces it leaves behind. One of the most compelling pieces of indirect evidence for dark matter comes from the phenomenon of gravitational lensing, a striking consequence of Einstein's theory of general relativity. Gravitational lensing occurs when the gravity of a massive object, like a galaxy or cluster of galaxies, bends the path of light from a more distant source. This bending creates distorted, magnified, or even multiple images of the background object, much like a glass lens does. When astronomers measure the extent of this lensing, they find something peculiar. The visible mass of the galaxy or cluster is far too small to account for the degree of light bending. The gravitational pull needed to create these effects is immense, far greater than what observable matter could produce. This discrepancy points to the presence of an unseen mass surrounding and permeating these galaxies. Dark matter, though invisible, exerts a gravitational influence that reveals itself through these cosmic distortions, allowing astronomers to see its effects, even if they can't directly observe the matter itself. Another key piece of evidence for dark matter comes from the rotation curves of galaxies. Graphs showing the velocity of stars and gas as a function of their distance from the galactic center. In a galaxy governed solely by the visible matter, you'd expect the stars further from the center to orbit more slowly, similar to how planets in our solar system move. This is because gravity weakens with distance, and the mass producing the gravitational pull would primarily reside in the dense star-filled core. However, observations tell a very different story. When Vera Rubin and her colleagues measured the rotation speeds of stars in spiral galaxies, they found that these velocities remain nearly constant, even at great distances from the galactic center. This flat rotation curve implies the existence of a vast, unseen halo of mass, extending far beyond the visible stars. Without this invisible matter, the stars at the outskirts of the galaxy should be flung off into space, unable to maintain their high velocities. The logical conclusion: a massive halo of dark matter envelops the galaxy, providing the necessary gravitational pull to stabilize the outer stars. Gravitational lensing and galaxy rotation curves are two sides of the same coin, each offering a glimpse of dark matter's pervasive role in the universe. Together they form a consistent narrative. There is far more to the cosmos than meets the eye. Dark matter doesn't just shape individual galaxies, it influences entire clusters. In fact, gravitational lensing studies of massive galaxy clusters reveal intricate maps of dark matter's distribution, showing how it congregates in enormous structures that act as the scaffolding of the universe. These clusters themselves are stabilized by dark matter's immense gravitational influence, just as individual galaxies are. These indirect observations highlight the ingenuity of science. Without the ability to see or directly interact with dark matter, researchers rely on its gravitational footprints to trace its existence. Each distorted image and unexpected star velocity is a clue bringing us closer to understanding the unseen. While the nature of dark matter remains elusive, these pieces of evidence confirm its presence beyond reasonable doubt. Dark matter is not.
Wait, don't scroll. You're missing out on your free TradingView Premium account. TradingView just turned 15 and they're giving away premium desktop access for free. I already have mine. Go get yours.
Dark matter is enigmatic, not just because it's invisible to the naked eye, but because it interacts so weakly, if at all, with ordinary matter. This makes its direct detection an extraordinary challenge, requiring experiments of unparalleled sensitivity and precision. Despite these hurdles, scientists have devised ingenious methods and cutting-edge facilities to attempt what might seem impossible, capturing evidence of dark matter directly. The Large Hadron Collider, smashing particles to unveil mysteries. The Large Hadron Collider, LHC, located at CERN in Geneva, is the world's most powerful particle accelerator. With its 27-kilometer ring buried underground, the LHC smashes protons together at nearly the speed of light, creating conditions similar to those that existed moments after the Big Bang. These high-energy collisions produce a cascade of particles, which are meticulously analyzed by detectors to search for anomalies, potential fingerprints of dark matter. Scientists at the LHC are particularly interested in detecting WIMPs, weakly interacting massive particles, a leading candidate for dark matter. The theory suggests that WIMPs might be created during these collisions. If WIMPs exist, they could appear as missing energy in the data escaping the detectors, without interacting much like neutrinos. While no conclusive evidence for dark matter has yet emerged from the LHC, the experiments have provided valuable constraints, narrowing the range of possible properties that dark matter could possess. The search continues with upgraded detectors and refined collision parameters as researchers hope to one day spot dark matter particles among the debris of their high-energy collisions. Deep underground, shielded from cosmic rays and other background noise, lies the large underground xenon LUX detector, one of the most sensitive instruments ever built to hunt for dark matter. Located in the Sanford Underground Research Facility in South Dakota. LUX relies on a tank filled with ultra-pure liquid xenon to detect the faintest interactions between dark matter particles and normal matter. The principle is straightforward but ambitious. If a dark matter particle passes through the detector and collides with a xenon nucleus, it will produce a minuscule flash of light scintillation and a small ionization signal. These signals are then captured by ultra-sensitive photomultiplier tubes capable of detecting even the faintest whispers of activity. Although LUX has not yet observed definitive evidence of dark matter, its results have set new benchmarks for sensitivity, helping to rule out certain theoretical models. Its successor, LUX Zeppelin LZ, is even more advanced with a larger detector and enhanced capabilities to sift through the cosmic silence in search of dark matter's elusive presence. Beyond the LHC and LUX, numerous other experiments contribute to the hunt for dark matter. Projects like Xenon 1T in Italy, PICO in Canada, and Super CDMS in the United States employ different approaches from cryogenic detectors to bubble chambers to maximize the chances of detection. Each of these experiments tackles a specific aspect of the dark matter puzzle, reflecting the global collaboration and interdisciplinary innovation required to confront this profound challenge. The diversity of techniques ensures that even if one method fails, others may succeed in uncovering dark matter's secrets. The direct detection of dark matter would mark a watershed moment in physics, confirming the existence of a previously invisible component of the universe. It would provide not only answers to long-standing questions, but also open doors to entirely new realms of understanding. For now, the search continues, a testament to humanity's unyielding curiosity and determination to reveal the unseen forces shaping the cosmos. Detecting dark matter is one of the greatest challenges in modern physics. By its very nature, dark matter defies direct observation. It does not emit, absorb, or reflect light, nor does it interact with electromagnetic forces. Its presence can only be inferred through its gravitational effects, making the search akin to hunting shadows in a darkened room. Yet these obstacles have not deterred scientists. Instead, they have fueled ingenuity, pushing the boundaries of technology and theoretical physics. The prevailing hypothesis suggests that dark matter interacts only through gravity and possibly the weak nuclear force. If true, this means that dark matter particles pass through ordinary matter almost entirely unnoticed. For context, billions of dark matter particles could be streaming through your body at this very moment, leaving no trace of their passage. This weak interaction necessitates detectors of extraordinary sensitivity. These instruments must distinguish potential dark matter signals from a cacophony of background noise, including cosmic rays, neutrinos, and even natural radioactivity in the Earth itself. To overcome this, experiments are often placed deep underground or in remote locations to minimize interference. The pursuit of dark matter demands cutting-edge technology, which comes with significant costs. Facilities like the Large Hadron Collider and underground detectors like LUX or Xenon require immense financial and logistical support. Furthermore, the sheer complexity of these instruments means that even minor malfunctions can delay research for months or years. For instance, Liquid xenon detectors must maintain extreme purity to avoid contamination that could mimic dark matter interactions. Achieving this level of precision requires meticulous engineering and constant monitoring, making every experiment a balancing act between innovation and practicality. One of the greatest challenges in the hunt for dark matter is the uncertainty surrounding its nature. While theories like WIMPs, weakly interacting massive particles, dominate the conversation, other candidates such as axions, sterile neutrinos, and primordial black holes offer competing possibilities. Each theory demands a different experimental approach, dividing resources and efforts. Moreover, if dark matter does not conform to these existing models, scientists may be searching in the wrong direction entirely. The possibility that dark matter interacts via unknown forces or consists of particles beyond the standard model of physics remains an ever-present challenge, forcing researchers to constantly reevaluate their assumptions. Dark matter is not evenly distributed throughout the universe. It clusters in halos around galaxies and galaxy clusters, but its density varies significantly depending on location. Detecting dark matter on Earth might therefore be akin to searching for a single grain of sand in an entire desert, a problem of scale and probability. This uneven distribution also complicates experimental timing. Certain experiments rely on the Earth's motion through the galaxy to detect variations in dark matter, particle flux. Such seasonal or directional signals are faint and require years of data collection to confirm. Despite these formidable challenges, the search for dark matter continues with unwavering determination. Each failed experiment provides critical data, narrowing the field of possibilities and refining our understanding. These incremental advances are essential steps in the scientific process, building toward an eventual breakthrough. The global effort to detect dark matter involves thousands of researchers, engineers, and theorists working collaboratively across disciplines. New experiments like the upcoming Lux-Zeppelin LZ detector and advancements in neutrino observatories are poised to push the limits of sensitivity even further. Theoretical physicists, meanwhile, continue to develop models that integrate dark matter into the broader framework of cosmic evolution, offering fresh perspectives and potential avenues for detection. The stakes are high. Detecting dark matter would not only confirm its existence, but also revolutionize our understanding of the universe. It could illuminate the processes that shaped galaxies, provide insights into the early moments of the cosmos, and reveal connections between the macroscopic structure of the universe and the microscopic world of particles. Above all, the pursuit of dark matter represents the essence of human curiosity. It is a testament to our drive to understand the unseen, to answers that bind the cosmos together, and to push beyond the boundaries of what is known. The standard model of particle physics is one of the most successful theories in science. It describes the fundamental particles, quarks, leptons, and bosons, and the forces that govern their interactions. The electromagnetic weak and strong nuclear forces. With the discovery of the Higgs boson in 2012, the standard model seemed complete, offering a coherent explanation for much of the observable universe. However, there's one glaring problem: the standard model doesn't account for dark matter. While it elegantly explains the behavior of ordinary matter, it fails to include the mysterious substance that constitutes roughly 27% of the universe's mass energy content. This discrepancy has placed the standard model under immense strain, compelling scientists to search for extensions or entirely new frameworks. One of the clearest ways dark matter challenges particle physics is through its gravitational effects. The standard model has no particle capable of producing the massive gravitational influence attributed to dark matter. Neutrinos, the only standard model particles that interact weakly and are electrically neutral, were once considered candidates. However, their tiny masses and high velocities render them incapable of explaining the observed behavior of galaxies and galaxy clusters. Dark matter's gravitational effects indicate it must consist of a new type of particle, one that interacts weakly with ordinary matter, but has sufficient mass to shape the cosmos. This requirement forces researchers to look beyond the standard model for answers. Dark matter
Bro, ऐसे chances ना लो, ये लो, just we लो.
It does not emit, absorb, or reflect light, making it undetectable through traditional methods. This property places it outside the realm of particles, like electrons or photons, which are central to the standard model. The absence of electromagnetic interaction raises profound questions about the nature of dark matter. Does it belong to an entirely new class of particles? Does it interact via unknown forces? These possibilities hint at physics beyond the established paradigm, requiring theoretical innovation. Dark matter's existence suggests that the standard model is incomplete. Several theories aim to bridge this gap, including supersymmetry, SUSY. This theoretical framework extends the standard model by proposing a partner particle for each known particle. In this context, the lightest supersymmetric particle, LSP, such as a neutralino, is a promising dark matter candidate. However, the failure of experiments like the Large Hadron Collider to detect supersymmetric particles has cast doubt on this theory. Hidden sectors. Some models propose that dark matter resides in a hidden sector, a parallel universe of particles and forces that interacts with ordinary matter only through gravity or other weak interactions. This idea introduces exotic particles like axions and sterile neutrinos as potential dark matter candidates. Modified gravity. While not a particle-based solution, some physicists explore the idea that our understanding of gravity itself may be incomplete. Theories like modified Newtonian dynamics, MOND, challenge the need for dark matter by suggesting that gravity behaves differently on cosmic scales. However, these theories struggle to match the evidence provided by phenomena like gravitational lensing. Dark matter doesn't just challenge the standard model, it opens a window into uncharted territory. If dark matter particles are discovered, they could revolutionize our understanding of the universe's evolution, the forces that govern it, and the underlying structure of reality itself. Such a breakthrough might unify disparate areas of physics from the quantum scale to cosmological structures, offering insights into long-standing mysteries like the nature of gravity and the origins of the universe. Among the myriad theories proposed to explain dark matter, WIMPs, or weakly interacting massive particles, stand as the frontrunners. WIMPs are hypothetical particles predicted to have masses much greater than that of protons, yet they interact only weakly with ordinary matter. This means they can pass through stars, planets, and even our bodies without leaving a trace. The appeal of WIMPs lies in their compatibility with the thermal relic hypothesis. In the early universe, particles were created and annihilated in high-energy interactions. As the universe expanded and cooled, most of these particles decayed or annihilated, but some remained. The predicted abundance of WIMPs aligns closely with the observed density of dark matter, making them a compelling candidate. Another promising dark matter candidate is the axion, a hypothetical particle much lighter than WIMPs. Axions arise from solutions to theoretical problems in the standard model, specifically the strong CP problem, which involves the behavior of quarks and gluons in quantum chromodynamics, QCD. Unlike WIMPs, axions are extraordinarily light and interact extremely weakly with both matter and radiation. What makes axions fascinating is their potential to form a vast invisible field permeating the universe. These particles could also account for the observed rotation curves of galaxies and other gravitational phenomena attributed to dark matter. Ongoing experiments such as the Axion Dark Matter Experiment, ADMX, aim to detect axions by searching for in a crucial way. They do not interact via any of the known forces except gravity. These heavier, sterile counterparts of regular neutrinos could constitute dark matter if they were produced in sufficient abundance in the early universe. Sterile neutrinos are intriguing because their decay could emit detectable X-rays. Observations of unexplained X-ray emissions from galaxies and galaxy clusters have fueled interest in this candidate, though no definitive evidence has yet emerged. Primordial black holes, dark matter without particles. A more unconventional candidate for dark matter is primordial black holes, PBHs. Unlike particle-based explanations, PBHs are compact objects that might have formed shortly after the Big Bang. These black holes could range in size from microscopic to many times the mass of the Sun, and might account for at least part of the universe's dark matter. Although PBHs do not require exotic new particles, their presence would profoundly impact our understanding of cosmology and the early universe. Studies of gravitational lensing and cosmic background radiation are ongoing to determine whether PBHs could explain the observed effects of dark matter. The diversity of dark matter candidates reflects the breadth of the challenge. Beyond WIMPs, axions, sterile neutrinos, and primordial black holes, researchers explore other possibilities, including superfluid dark matter, a theory suggesting that dark matter could form a quantum superfluid, influencing gravity in unique ways. Fuzzy dark matter, extremely light particles with wave-like properties that could form large-scale structures. Self-interacting dark matter, particles that interact with themselves but not with ordinary matter, potentially explaining certain galactic phenomena. Each candidate represents a different facet of the dark matter puzzle. WIMPs dominate collider and underground detection efforts, while axions and sterile neutrinos push the boundaries of particle physics. Primordial black holes and exotic theories challenge the very concept of what dark matter might be. The search for these candidates is a testament to the creativity and adaptability of science. Whether dark matter turns out to be a familiar particle or something entirely unexpected, its discovery will revolutionize our understanding of the cosmos and the laws that govern it. The discovery of dark matter would revolutionize our understanding of the universe's history and structure. Currently, dark matter is considered the invisible scaffolding upon which galaxies and larger cosmic structures are built. By unraveling its nature, we could answer fundamental questions about how the universe formed, evolved, and reached its present state. In the early universe, shortly after the Big Bang, dark matter played a crucial role in shaping the cosmic web. While ordinary matter interacted with light and radiation, dark matter remained unaffected by electromagnetic forces, allowing it to clump together under gravity. These clumps served as gravitational wells, pulling ordinary matter into them and forming the seeds of galaxies. Discovering the properties of dark matter would refine our models of these early processes, offering a clearer picture of how galaxies, stars, and planets emerged. The universe is structured in a vast, interconnected web of galaxies, clusters, and voids. This cosmic web is shaped by the gravitational influence of dark matter. Without it, these structures would not exist as we observe them today. If dark matter's properties were identified, such as its mass interaction strength or particle behavior, scientists could better simulate the universe's large-scale evolution. These insights would bridge gaps in our understanding of how cosmic structures formed over billions of years and how they continue to evolve under the influence of both dark matter and dark energy. Dark matter's role isn't limited to the past. It also shapes the future. The gravitational pull of dark matter counters the expansive force of dark energy, which drives the acceleration of the universe's expansion. Understanding the balance between these forces could help predict the ultimate fate of the cosmos. If dark matter interacts in ways we don't yet understand, it could influence whether the universe continues expanding forever eventually freezing in a heat death or contracts in a big crunch. Alternatively, if dark matter decays over cosmic timescales, its diminishing influence could allow dark energy to dominate, leading to even more rapid acceleration and a big rip. By identifying and studying dark matter, physicists could refine these scenarios, offering profound insights into the universe's destiny. Dark matter discovery would unify two seemingly disparate realms of physics, the quantum and the cosmic. At its core, dark matter likely consists of particles governed by quantum mechanics. Yet its influence is felt on the largest scales, shaping galaxies and the universe itself. This connection might lead to breakthroughs in other areas of science, such as particle physics. Discovering dark matter, particles could expose new forces or symmetries in nature, leading to extensions of the standard model. Astrophysics understanding, dark matter would refine models of star formation, galaxy dynamics, and black hole behavior. Cosmology insights into dark matter could provide clues about the universe's earliest moments, potentially shedding light on inflation or other processes near the Big Bang. Beyond the scientific implications, discovering dark matter would profoundly impact how humanity views its place in the cosmos. It would reveal that much of the universe consists of something fundamentally different from the matter that makes up our bodies, our planet, and everything we've ever known. This realization could deepen our sense of connection to the cosmos, emphasizing that we are part of a much larger, more mysterious whole. Perhaps the most exciting implication of discovering dark matter lies in the doors it could open. Historically, every major scientific breakthrough has led to unexpected discoveries. Electricity paved the way for modern
Still looking for the ultimate AI tool? Hailuo AI takes your AI experience to the next level. Just type your idea and click generate. Your imagination will come to life in seconds. Whatever you imagine, we bring it to the screen. No skills needed, no effort, no budget. Sign up for free and try it now.
About solving a mystery. It's about expanding the boundaries of human knowledge, venturing into the unknown, and uncovering truths that could redefine our understanding of existence itself. Dark matter plays a fundamental role in cosmology, the study of the origin, evolution, and structure of the universe. Its gravitational influence serves as the backbone of cosmic structures, dictating how galaxies form, cluster, and evolve over billions of years. Without dark matter, the cosmos as we know it would not exist. Understanding dark matter is therefore essential to refining our models of the universe's formation and its large-scale behavior. In the early universe, just after the Big Bang, dark matter began to clump together under gravity, forming dense regions that acted as seeds for galaxy formation. Ordinary matter composed of atoms was initially scattered by intense radiation, but eventually fell into these dark matter wells, creating the galaxies and clusters we see today. Without dark matter, this possibly slow, leaving a universe largely devoid of structure. Exploring dark matter is key to unraveling these early cosmic events. The universe is expanding, a fact first discovered by Edwin Hubble in the 1920s. Over time, this expansion has been found to be accelerating, driven by a mysterious force called dark energy. Dark matter and dark energy together dominate the universe, comprising approximately 95% of its total mass energy content. Their interplay shapes the dynamics of the cosmos. Dark matter slows the expansion through its gravitational pull. Energy pushes against it, driving acceleration. Understanding dark matter is critical to deciphering this. The tug of war. How dark matter and dark energy interact influences the rate of cosmic expansion. Precise knowledge of dark matter's properties, its density distribution and interactions would allow cosmologists to make more accurate predictions about the universe's future trajectory. The ultimate fate of the universe. Whether the cosmos ends in a big freeze, big crunch, or big rip depends largely on the role and behavior of dark matter over cosmic timescales. The lambda cold dark matter is the prevailing framework in cosmology. It describes a universe composed of dark energy, dark matter, and ordinary matter. While lambda cold dark matter has been extraordinarily successful in explaining observations like the cosmic microwave background, radiation, and large-scale galaxy distributions, it remains incomplete without a deeper understanding of dark matter. Structure formation, simulations of galaxy and cluster formation depend heavily on assumptions about dark matter's properties. Better understanding could resolve discrepancies between observed and simulated galaxy distributions, small-scale anomalies. The lambda cold dark matter model struggles to explain certain small-scale phenomena like the observed density profiles of dark matter in galaxies. The cusp core problem. A deeper understanding of dark matter could address these inconsistencies. Studying dark matter may also provide insights into the universe's infancy. Shortly after the Big Bang, conditions were so extreme that matter and energy were indistinguishable. Dark matter's behavior during this epoch could reveal clues about the inflationary era, the rapid expansion of the universe immediately following the Big Bang. Baryogenesis, the process by which ordinary matter came to dominate over antimatter. Rionization, the period when the first stars and galaxies began to form. Reionizing the universe's neutral hydrogen. By connecting the properties of dark matter to these events, cosmologists could fill gaps in our understanding of the universe's earliest moments. Dark matter research also has profound implications for understanding dark energy, the force driving cosmic acceleration. While these two phenomena are distinct, they are deeply intertwined in shaping the universe's fate. Studying dark matter may reveal new physics that unifies them, providing a more complete picture of the universe's mass energy content and its ultimate destiny. Understanding dark matter would mark a paradigm shift in cosmology, akin to Copernicus' heliocentric model or Einstein's theory of general relativity. It would not only refine our knowledge of the universe's expansion, but also reveal the fundamental processes that govern the cosmos. By answering the question of dark matter, we edge closer to answering the larger questions. Where did we come from? Where are we going? And what is the true nature of reality? The discovery of dark matter would be a watershed moment for particle physics, opening a door to realms of knowledge far beyond the Standard Model. While the Standard Model has been remarkably successful in describing the known particles and forces, it cannot account for the mysterious substance that makes up 27% of the universe. This glaring gap suggests the existence of entirely new particles forces or symmetries that extend the boundaries of our current understanding. If dark matter is composed of particles, discovering its true nature could revolutionize our understanding of the subatomic world. Among the most promising avenues are WIMPs, weakly interacting massive particles. As leading candidates, WIMPs would represent a new class of particles interacting via weak nuclear forces. Their discovery could reveal new interactions and extensions to the Standard Model, such as supersymmetry, which posits the existence of partner particles for all known particles. Axions. The discovery of axions would solve not only the dark matter mystery, but also the strong CP problem in quantum chromodynamics. Axions could provide a bridge between particle physics and cosmology, unveiling connections previously thought unrelated. Sterile neutrinos. These hypothetical particles, unlike their Standard Model counterparts, would only interact through gravity. Detecting sterile neutrinos could expand our knowledge of neutrino physics and offer insights into the behavior of other elusive particles. Each of these particles represents a possible paradigm shift revealing interactions or dimensions of nature that are currently hidden from view. Dark matter could point to the existence of previously unknown forces or interactions. For example, dark sector physics. Some theories propose that dark matter interacts with itself through dark forces mediated by particles analogous to photons in the visible universe. Detecting these forces could unveil an entirely new layer of reality, a dark sector that exists parallel to our observable universe. Fifth, force of nature. If dark matter interacts with ordinary matter in unexpected ways, it might hint at a new fundamental force beyond the four currently known: gravitational, electromagnetic, strong nuclear, and weak nuclear forces. These discoveries would fundamentally alter our understanding of how the universe operates, potentially unifying disparate phenomena under a broader theoretical framework. One of the most profound implications of dark matter research lies in its potential to connect quantum mechanics and general relativity. Two pillars of modern physics that remain theoretically incompatible. Dark matter operates on both quantum and cosmic scales, offering a rare opportunity to study phenomena that could unify these frameworks. If dark matter consists of quantum particles with wave-like properties, its behavior might illuminate how quantum effects manifest on macroscopic gravitational scales. Understanding dark matter's gravitational effects could provide insights into quantum gravity, bringing us closer to a theory of everything. The hunt for dark matter has driven advancements in technology that benefit particle physics more broadly. High-energy experiments like those at the Large Hadron Collider (LHC) are continually upgraded to achieve greater sensitivity, paving the way for discoveries beyond dark matter. Innovations in detector design, such as cryogenic techniques and ultra-pure materials, are already being applied to explore other unanswered questions in physics. These advancements not only enhance our ability to detect dark matter, but also improve our capacity to explore phenomena like neutrino oscillations, proton decay, and the asymmetry between matter and antimatter. The discovery of dark matter would necessitate extending the Standard Model to include new particles interactions and symmetries. Such an extension could reveal connections between seemingly unrelated phenomena, such as dark matter and the Higgs field, provide a framework for understanding other cosmic mysteries like dark energy or the origins of matter-antimatter asymmetry, offer insights into the conditions of the early universe, such as the processes that occurred during and after the Big Bang. The breakthroughs in particle physics spurred by dark matter research would ripple across multiple disciplines from astrophysics to cosmology. These discoveries could redefine fundamental concepts such as mass force and even the nature of reality itself. As our theoretical frameworks evolve, so too will our ability to answer deeper questions about existence. As we conclude this journey through the unseen universe, one truth remains abundantly clear: dark matter is one of the greatest mysteries of our time. Its discovery and understanding hold the potential to reshape not only physics, but our very perception of reality. Yet for all that we've explored, its gravitational fingerprints, its hypothesized particles, and its role in the evolution of the cosmos, dark matter remains tantalizingly elusive. This mystery is a reminder of the vastness of the
This is the lost world of the dinosaurs.
the fundamental nature of existence itself. The ongoing quest to understand dark matter is a testament to human curiosity and ingenuity. It represents the best of science, a relentless pursuit of knowledge, driven by the belief that the answers lie just beyond our reach. With each experiment, each observation, and each theoretical breakthrough, we inch closer to uncovering the secrets of the cosmos. But dark matter is more than a scientific challenge. It's a source of inspiration. It invites us to dream, to question, and to wonder what lies hidden in the fabric of the universe. What new realms of physics await discovery? How will these insights transform our understanding of the cosmos and of ourselves? The future of dark matter research is bright, filled with promise and potential. Advancements in technology, from more sensitive detectors to next-generation particle accelerators, bring us closer to direct detection. New telescopes and space missions will map the cosmos with unprecedented precision, revealing the subtle influences of dark matter on galaxies and beyond. Meanwhile, theoretical physicists continue to push the boundaries of what is possible, exploring ideas that might seem unimaginable today, but could become the discoveries of tomorrow. Each step forward in the hunt for dark matter deepens our understanding of the universe, reminding us that the pursuit of knowledge is never truly finished. As we unravel this mystery, we'll inevitably uncover new questions, new frontiers to explore, new challenges to face, and new wonders to marvel at. So as we look to the future, let us embrace the mystery of dark matter. Let it remind us of the infinite possibilities that lie within the cosmos, waiting to be discovered. The journey to understand dark matter is far from over, but every step we take brings us closer to answering the fundamental questions of existence. What is the universe made of? Where did it come from? And what is our place within it? In the end, the greatest discoveries often begin with the simplest yet most profound realization: the universe is far more mysterious than we could ever imagine. And that mystery in itself is the ultimate source of wonder. Can science fiction become reality? This question isn't just for fans of novels or movies. It's one of humanity's greatest mysteries. The discovery of extraterrestrial life, and possibly making first contact, would undoubtedly rank as one of the most monumental scientific breakthroughs in history. Yet the universe seems to act like an enormous wall, putting up countless barriers between us and other potential civilizations. Despite these challenges, we continue to search for answers among the stars. Are we truly alone in the cosmos, or is intelligent life waiting somewhere out there, just beyond our reach? The Arecibo message. Our first attempt in 1974. Something incredible happened. At the Arecibo Observatory in Puerto Rico, we sent a powerful radio message deep into space. This wasn't just a casual hello. It was a carefully crafted message packed with information about Earth, our location, basic biology, and even the structure of our DNA. The message was aimed at a star cluster called M13, located about 25,000 light-years away. If there's intelligent life out there, this was our way of saying, "We're here. Are you?" It was humanity's first direct attempt to communicate with a possible alien civilization. But here's the catch: even traveling at the speed of light, that message won't reach its destination for another 25,000 years. And if anyone replies, well, we'll have to wait another 25,000 years to hear back. It's a bold move when you think about it. We're sending out a message with no guarantee that anyone is listening. But it raises the ultimate question: are we really alone in the universe? Is there life out there? So how likely is it that someone or something is out there waiting for our message? The answer seems obvious. Yes. Life on Earth began almost as soon as our planet formed. If it could happen here, why not somewhere else? Astronomer Frank Drake tried to tackle this question with a groundbreaking approach. He created the Drake equation, a formula designed to estimate the number of intelligent civilizations in our galaxy. When the equation was first introduced, scientists projected that there could be about 10,000 civilizations capable of communication. Since then, our understanding of the universe has grown dramatically. For one, we've discovered exoplanets, planets orbiting stars outside our solar system. At last count, astronomers have confirmed over 5,500 exoplanets, and they believe that's just the tip of the iceberg. What's more, scientists now estimate there may be more planets than stars in the cosmos. If the universe is so good at making planets, it stands to reason that it might also create the conditions for life. Even if life is rare, the sheer size of the universe offers countless opportunities for it to exist. The odds seem to favor the idea that intelligent civilizations are out there somewhere. But here's the mystery. If there's so much potential for life, why haven't we found any evidence yet? The vastness of the cosmos. If the universe is brimming with possibilities for life, then why haven't we found anyone yet? One answer might lie in the sheer size of the cosmos. It's hard to wrap our heads around just how vast everything is. Take our own galaxy, the Milky Way. It's so big that even traveling at the speed of light, a signal sent from one end to the other would take 100,000 years to arrive. We're out here in the suburbs of the galaxy, about 75,000 light-years from its edge. That's a long way from any cosmic neighbors. Now think about the Arecibo message. After 45 years, it has only covered a fraction of the distance to its target. At this rate, communication with another civilization becomes a waiting game on a scale we can barely imagine. Even if there are thousands of intelligent civilizations in the galaxy, the distance between us might be so immense that we'll never hear from one another. The laws of physics don't make it easy. Nothing can travel faster than the speed of light. So no matter how advanced we become, those vast distances are a roadblock we can't get around. But that hasn't stopped us from trying. Projects like Breakthrough Listen are using the most advanced technology on Earth to scan the skies. With radio telescopes and optical sensors, they're focusing on the stars and galaxies closest to us, searching for any signs of intelligent life. So far, it's been quiet, like waiting for a call that never comes. But that doesn't mean no one's out there. It just means we're still looking. The patience of the search. Searching for extraterrestrial life is a bit like looking for a needle in a cosmic haystack. Imagine this: even if there are 10,000 intelligent civilizations in the galaxy, there are roughly 250 billion stars out there. That's like trying to find one specific house in a city of 25 million. It's an enormous challenge, and it's going to take time. Even if we do eventually hear something, there's another problem: time itself. Imagine a civilization sends us a signal, but by the time it reaches us, they're already gone. Civilizations rise and fall, and the timeline of the universe is so vast that we might simply be missing each other. Earth has been around for 4.5 billion years, but humans, we've only been here for about 300,000 years. In cosmic terms, we're late to the party. The universe is 13.8 billion years old, meaning other civilizations could have existed billions of years before us. They might have reached incredible technological heights, only to disappear long before we even began searching. But this doesn't mean we should give up. Our search is just getting started. Breakthrough Listen, for instance, is focusing on the 1/700 stars nearest to us, using cutting-edge technology to catch even the faintest signal. If there's life out there, projects like these are our best hope of finding it. For now, though, we wait, and in the grand timeline of the universe, patience might be the most important tool we have. The Kardashev scale, measuring civilizations. If intelligent civilizations exist, how advanced could they be? To answer this, scientists use something called the Kardashev scale, which ranks civilizations based on their ability to harness energy. Type 1 civilizations can use all the energy available on their home planet. Type 2 civilizations can harness the energy of their entire solar system. Type 3 civilizations are the ultimate powerhouses capable of using energy from an entire galaxy. And where do we stand? Well, we're not even at Type 1 yet. Humanity is somewhere around Type 0.7, still learning how to fully utilize the energy resources of Earth. but the Kardashev scale offers a glimpse of what might be possible if a civilization survives long enough to keep advancing. Imagine a Type 2 civilization. They might build something like a Dyson sphere, a structure that surrounds a star and captures nearly all of its energy. First proposed by physicist Freeman Dyson, this concept represents technology so advanced it's almost hard to imagine. If such structures exist, they would block most of the star's light, leaving only faint trace. Lack of evidence doesn't mean the universe isn't teeming with life. It just means we haven't found it yet. Are we late to the party? The universe is old, 13.8 billion years old, to be exact. Civilizations could have risen and fallen long before Earth even formed. It's humbling to think that while humans have been here for about 300,000 years, that's just a blink in the timeline of the cosmos. Some scientists believe this might explain why we haven't made contact yet. It's possible that intelligent civilizations existed billions of years ago, but are now long gone. Imagine a message finally reaching us from another world only for us to discover that the senders vanished ages ago. It's like trying to join a party, only to find out it ended before you even got the invitation. But there's another possibility. What if we're the early ones? Earth may seem ancient to us, but in the grand timeline of the universe, we could be among the first intelligent species to emerge. If that's true, it's not just about waiting for others to contact us. It's about deciding what kind of civilization we want to be. Right now, humanity is at a crossroads. We're building the tools to explore the cosmos, but we're still learning how to take care of our own planet. If we ever hope to reach the levels of a Type 1 or Type 2 civilization, we'll need to survive the challenges of today. Our search for extraterrestrial life is about more than just finding aliens. It's about understanding our place in the universe. Whether we're latecomers to the cosmic party or among the first civilizations to emerge, the quest itself is a testament to human curiosity and resilience. Projects like the Breakthrough Listen initiative remind us that even if the universe is vast and the odds seem impossible, we are determined to keep looking. Every discovery, from exoplanets to radio signals, brings us closer to answering the question, are we alone? But maybe the most important takeaway is this: the universe doesn't owe us answers. The search for intelligent life might take decades, centuries, or even longer. Yet by exploring the cosmos, we're not just searching for others, we're learning about ourselves. Humanity is still in its infancy on the cosmic scale, but we have the tools and the ambition to grow. One day we might become the advanced civilization others are searching for. Until then, we'll keep listening to the stars, sending out our messages, and dreaming of the day we finally hear something back. For billions of years, the universe may have witnessed the rise of countless intelligent civilizations, only to see them obliterated by ruthless filters, from devastating gamma-ray bursts to their own self-destruction. Can Earth overcome the cosmic filters and rise to an advanced civilization? Or will humanity repeat the fate of extraterrestrial civilizations that have vanished in the flow of the universe? If extraterrestrial life exists, the question arises whether their forms and environments would be similar to those on Earth. This idea draws from the concept that certain conditions, whether astrophysical, biological, or societal, act as filters that limit the emergence and longevity of advanced civilizations. Possible filters include cataclysmic events, astrophysical phenomena, or self-destructive behaviors inherent to intelligent societies. If extraterrestrial life exists, its forms and environments might not necessarily resemble those on Earth. Life could evolve in diverse ways depending on the unique conditions of each planet. The variety of planetary environments and the adaptability of life make it plausible that extraterrestrial beings might have different biochemistries and physical characteristics. Rocky planets like Earth are considered ideal for supporting life due to their specific conditions. However, these planets are delicate and susceptible to various threats. And this fragility means the universe could filter out intelligent life quickly. One significant threat comes from violent stellar events, such as gamma-ray bursts, which are powerful enough to sterilize planets over vast cosmic distances, potentially affecting entire galaxies. Imagine this: a massive star explodes in our galaxy, the Milky Way, sending a deadly burst of energy hurtling toward our planet. This is a gamma-ray burst, the most powerful explosion since the Big Bang. There are no signs that something catastrophic is about to happen, and then it strikes. The radiation surges, heating the upper atmosphere. Our ozone layer is scorched across the atmosphere. Humans are incinerated by radiation 100 times the lethal dose. As the ozone layer thins, temperatures rise worldwide. This triggers storms, tsunamis, and hurricanes. Most life on land and in water is incinerated. This may sound like science fiction, but if a gamma-ray burst from 100 light-years away struck Earth, it could happen. Even if intelligent species manage to survive these natural occurrences, there is another risk: self-destruction. Drawing from our own experiences on Earth, the development of technology has given us the capability to alter our climate and create weapons of mass destruction. This self-destructive potential poses a serious risk for advanced civilizations. It is plausible that technologically advanced societies may have a brief existence, as evidenced by our own history. The short lifespan of advanced civilizations could be a reason why there are so few observable ones at this point in time. The possibility arises that many civilizations may have emerged, but their existence was short-lived due to self-inflicted challenges. This scarcity of long-lasting civilizations could explain the limited opportunities for communication with extraterrestrial beings. Discovering remnants of an extinct alien civilization could serve as a profound warning for humanity. If we were to find evidence of a civilization that destroyed itself through pollution or conflict, it would be akin to looking at our own potential future. This sobering realization could provide valuable lessons for us on Earth, emphasizing the importance of avoiding similar pitfalls. In our quest for understanding the cosmos, we can only hope that some advanced alien species have managed to navigate the challenges posed by the universe's potentially lethal filters, offering a glimpse of long-term survival and prosperity. If we are lucky, there may be an extraterrestrial civilization that will come to visit us in the future. Imagine making contact with aliens. Sounds cool, right? But hold on, are we assuming too much? We tend to think that aliens are just like us, but here's the twist: they're not. We might be imagining them based on what we know about life on Earth, assuming they live on planets like ours. But guess what? Most of the universe might not follow our life and planet rulebook. So could extraterrestrials even survive first contact with us and our planet? July 2019, a satellite on a test mission spotted a new alien world named GJ357d, about 31 light-years away. This super-Earth is over 6 times heavier than our cozy home planet. Now what's a super-Earth? A terrestrial planet, but bulked up with more mass. More mass means more gravity, creating a whole different vibe compared to our Earth. Imagine aliens living on a super-Earth. The gravity there could be super strong. They might not be tall, but I bet they'd be super strong. Super-Earths are just one of the many wild things the universe cooks up. Who knows what other surprises are out there? The possibilities are as vast as the cosmos itself. The universe is a vast playground, with planets of all shapes and sizes, orbiting stars of various types and sizes, forming countless configurations. This diversity opens up a world of possibilities for life that is much richer and more varied than we ever imagined. However, we need to break free from the idea that extraterrestrial life will resemble us. If we're expecting beings with 2 legs like ours, we might as well abandon that notion. The truth is, life out there could be radically different. Consider this scenario: an intelligent alien species in our cosmic neighborhood wants to say hi to us. But here's the catch. If that alien evolved on a super-Earth or circled a red star instead of a yellow one, its biology could be so alien that it might never set foot or tentacle on our planet. Looking at life on Earth, it seems like it's tailor-made for our specific temperature elements and environment. Now imagine an exoplanet with conditions conducive to life. It could still host life forms vastly different from what we're accustomed to. What if an alien world has a bit more potassium, is warmer than our average Earth, or has a thicker atmosphere? Each of these subtle differences could create an entirely distinct ecosystem. So the big question is, can an alien organism truly adapt to our ecosystem when it lands on Earth? It's a cosmic mystery waiting to unfold. In our solar system, Earth shines like a sapphire jewel. We go about our daily lives without knowing that trouble could be coming from deep space. The routes that Earth and most other things take around the Sun can be predicted. Most of the time things are quiet and easy, but sometimes they get crazy and violent. Earth can be hit by space rocks, zapped by dangerous space weather, jolted, jostled, and threatened by the object's energy and cosmic forces. The Earth is on a wild ride through space that is often very dangerous. When you're moving fast in on a predetermined path, you hope nothing crosses because there's nothing you can do. Rusty Schweikart used to be an astronaut, so he knows how dangerous things in space can be. During the Apollo 9 flight in 1969, he was in charge of the lunar module. He is sending out warnings about the risks of an asteroid named Apophis that is getting too close to be safe. Everyone noticed him right away because the probability of impact was quite high. In fact, it was significantly greater than any effect probability we had seen before. Schweikart has a scary example from real life that shows how bad an asteroid, even one smaller than Apophis, can be when it hits. June 30th, 1908, 7:15 a.m. A half-football field-sized object came hurtling down from space at about 34,000 miles per hour and made a stream of fiery gas behind it. Within minutes, the fireball hit Earth's atmosphere and burst violently near the Tunguska forest in Siberia. As a result, the explosion was the greatest ever recorded in the history of the planet. The explosion split the waves, which then set fire to 8 million trees in an area that was bigger than half of Rhode Island. Because the explosion happened in a place with few people, no one died directly from it. If that asteroid had hit just a few hours later, it would not have hit Siberia, but Europe. And if it had exploded in the air over one of Europe's biggest cities, 1 million people would have died. For the last 100 years, the Tunguska explosion has been shrouded in controversy. Many researchers now think an asteroid was the explosive trigger. Incredibly, it never even impacted the ground. Rather, it exploded 5 miles above Siberia's frozen ground. When it smacks into the lower atmosphere doing about 50,000 miles an hour, it's like an egg smashing on the concrete. Energy equivalent to 15 megatons of TNT was released in the Siberian explosion, making it 1,000 times greater than Hiroshima. Over a huge city, this would be catastrophic. NEOs, or near-Earth objects, were the name given by scientists to these trespassers. They are comets and asteroids' leftover debris from when the planets formed. The Oort cloud is a part of the Kuiper belt that extends past Neptune and is where comets travel. Between Jupiter and Mars, asteroids take a curved path. But their orbital trip isn't always routine. We don't have to worry too much about asteroids because they circle in a somewhat orderly belt between Mars and Jupiter. But when one gets away and all that mass and energy is going toward Earth, that's when the astronomers start to worry. It's not uncommon for cosmic debris to be jolted out of orbit and headed for Earth. The majority of it is evaporated by our planet's dense atmosphere. A larger object, however, is able to break through Earth's atmosphere and crash to the surface. Asteroids are a real and dangerous threat if you wish to look to the cosmos for the powers that would have us dead. Just like it did previously, it will happen again. 65 million years ago, an asteroid the size of a small city plummeted down from the sky. It exploded in the Yucatan Peninsula near the town of Chicxulub in Mexico with the force of 100 million megatons of TNT. Here we see Earth hurling billions of tons of its crust into space, creating a blanket that blocks out sunlight, destroying the food web at its roots, and killing off countless species. The ferocious impact is thought to have been a factor in the extinction of the dinosaurs. We can think of asteroids as being bad things, but if it were not for an asteroid, we wouldn't be here today. Our mammal ancestors were running on their foot trying to avoid being hors d'oeuvres for T-Rex. T-Rex gets taken out. Well, this opened up an ecological niche that allowed our mammal ancestors to evolve to something more ambitious than a route, and out comes the primates. And among the primates, we have people. But it's strange that the same kind of cosmic boulder that made it possible for humans to live could one day wipe us out. In 1998, Congress asked NASA to find all near-Earth objects that were at least half a mile across, and what they found was unsettling. There are more than 850 NEOs near our vicinity. These asteroids are our nearest and most dangerous space friends. Finding these near-Earth objects is a bit like keeping an eye on storms. As you watch it day after day, you get a better idea of its path and can figure out where it's going, how big it is, and how fast it would hit the Earth if it did. By using telescopic technologies, NASA's SpaceGuard survey has detected over 90% of all NEOs deemed harmful. These scary things could hit Earth with more power than all of the nuclear weapons on the world right now. Such an impact could trigger mass extinction. We wouldn't expect one to hit every few 100,000 or millions of years, but if one did, it could wipe out different parts of the population. So there are events that happen very rarely, but have big effects when they do. If they hit Earth, they would have impacts all over the world. They would not only wipe out a continent with very strong shock waves, but the debris would also be thrown into the air and land all over the planet, heating the air to 1,000 degrees. And all the vegetation all over the world where that happens would flash into flames. Smaller objects could also cause disasters, so Congress has asked NASA to find all NEOs with a diameter of 500 feet, which is as big as the Colosseum in Rome. A big object like that could wipe out a city or even a small state. Scientists are most worried about the asteroids they haven't found, yet not the ones they have found. Well, at the moment there are about 2,000 objects that we can't say for sure won't hit Earth. We now have the technology to keep near-Earth objects from ever hitting Earth again. We can now literally start to change the local solar system to make it better for our life. The question is whether or not we will end up like the dinosaurs. It's hard to believe that the Earth has been around for more than 4.5 billion years because it's been through a lot since it was born. Asteroids that come into our orbit every year keep hitting our world like a boxer, but one day Earth could be knocked out. We've learned that near-Earth objects fly by us all the time, and we're getting more and more able to change our surroundings to help us stay alive. A rock in space named Apophis. In 2004, this pock-marked rock, about 750 feet across, came close to Earth. Now it's scheduled to pass dangerously close to our planet again on Friday the 13th in April 2029. So in 2029, Apophis will get closer to us than our Rome communication satellites that circle the Earth. If you are in the right place, you will be able to see Apophis pass by the Earth with your own eyes. That's how close that rock is going to get. You won't even need binoculars. Over 99% of the time, Apophis will miss the Earth in 2029. However, if it passes the Earth at an exact distance of 1,893 miles, it may pass through a gravitational keyhole, a small area in space that is only a half-mile wide. If this happens, Apophis could be thrown off by the Earth's gravity, which could change its path. It could make it come back and hit Earth on April 13, 2036, 7 years later. The gravitational effect of the Earth would cause it to bend, cause the Apophis's orbit to enlarge to precisely the size which 7 years later it will come around and hit the Earth. At the present time, Apophis has 1 in 45,000 chance of delivering a deadly blow in 2036. It's one thing to say that there's a 1 in 45,000 chance that it will hit the Earth, but what you really want to know is if there's a 1 in 100, 1 in 10, or 1 in 1 chance that it will hit the Earth. We have to look at Apophis the same way we look at any natural disaster. You know, the date of the hit when it happened, and the angle of the orbit, so you can make a map. It starts in western Siberia, cuts across and down the Pacific Ocean near California, goes through Central America, and ends in Western Africa. Scientists have come up with a scary idea about where Apophis could strike. With a force of more than 1 million megatons of TNT, the asteroid could hit the Pacific Ocean off the coast of California. Such an impact would make a hole in the water 5 miles wide and 9,000 feet deep. This would cause tsunamis with waves up to 50 feet high to hit the coast, resulting in unimaginable human loss. If a rock 1,000 feet across hits the ocean, that's not a good thing? For that kind of thing, scientists are working on ways to stop such a cosmic strike from happening right now. A possible plan is to blow up an asteroid. But some people worry that this could make the problem worse by sending more pieces of the asteroid our way instead of just one. So the new goal for experts is to change the path of asteroids that could hit Earth. Change its velocity by a 10,000th of a mile per hour so that it will miss the Earth instead of hitting it. If we know about an asteroid far enough in advance, we can change its path. Although a space probe has landed on an asteroid in the past, the most challenging idea is launching a manned mission. Once landing on the rock, astronauts could mount a radio transponder to track its whereabouts. Now the United Nations plans to draft a treaty which will include who will be responsible for deflecting killer asteroids. If we are so careless that we keep doing nothing, even though we know this is going to happen, that will be a real crime. Any asteroid hitting the Earth will require international disaster response. In addition, training is required in disaster and emergency management institutions and the public regarding the asteroid threat. It is important that everyone is aware of the level of threats and the potential to eliminate this threat. Apart from all these, amateur astronomers can work together with scientists to defend our planet. Amateur astronomers can help identify smaller and potentially destructive asteroids hidden in the universe. So would you like to be an amateur astronomer? Who knows, maybe you can be one of the guards of our home. Far away in distant galaxies, a mysterious force is at work. 3 times a day, a strange flash lights up our sky. It's hundreds of times more powerful than all the world's nuclear weapons combined. But it wasn't made by people, and if one happens close enough to Earth, it could wipe out all life there. Most people on Earth don't know about the possible dangers in space. Imagine this. A huge star explodes in our galaxy, the Milky Way, sending a deadly burst of energy hurtling toward our planet. This is a gamma-ray burst, which is the biggest blast since the Big Bang. There are no signs that something bad is about to happen. And then it strikes. The radiation that is pumped up heats up the high atmosphere. Our layer of ozone heats up. Across the atmosphere, human beings burns to death from radiation 100 times the fatal dose. When the ozone layer gets thinner, temperatures rise all over the world. This makes storms, tsunamis, and hurricanes happen. Most life on the surfaces of land and water incinerates. This may sound like science fiction, but if a gamma ray burst from 100 light-years away hit Earth, it could happen. Gamma ray bursts are the most bright blasts in the universe. They must have a huge amount of power, because they are so far away, and yet still so bright. As much energy as the sun will give off in its full 10 billion year life. We know there are many planets and many stars in the universe, so gamma ray burst could have wiped out a lot of different cultures. In the 1960s, this strange blast of radiation was first seen. At first, because these gamma ray bursts are so bright. Most scientists thought they came from our own galaxy, the Milky Way. There are a few reasons for that. One of them is that if they are outside the galaxy, the energy is almost too much to believe. But back then, even the most powerful telescopes couldn't figure out where they were or how far away they were, because the burst only lasted a few seconds and then went away. But then scientists started to wonder about their afterglow. Most blasts in space leave a glowing trail behind that can last for days or even weeks. In the late 1990s, satellites with better optics and X-ray monitors were finally able to catch the afterglow of a gamma-ray burst. It became clear that gamma-ray bursts actually came from outside our galaxy millions and billions of light-years away. So their power had to be really out of this world. The brightness of the gamma-ray burst is the same as that of 1,000,000 trillion suns. This huge explosion could wipe out all life on Earth. But why do they happen? We are very sure that a common gamma-ray burst is caused by the death of a star that is at least 10 times the mass of the Sun. And these kinds of stars aren't very common. When a very big star dies, it falls apart and forms a black hole. Black holes are made when a mass of matter shrinks to a point where it is so dense that light can't get out. But experts think that some of the star resists getting sucked into the center of the black hole. As a result, a high-speed spinning disk of matter forms around it. In a matter of seconds, plasma jets shoot out from the poles where it spins. These beams of energy unleash dangerous gamma rays into space. At the same time, the gamma ray bursts are ejected. The collapsing star explodes or goes supernova to the extreme. Gamma ray bursts are so bright because they take a huge amount of power and focus it on a very small area of the sky. Only one of every 300 gamma ray bursts is directed toward us, so we only see one of those 300. Even if a gamma ray burst happened not 100 but 1,000 light years away, the Earth could still be destroyed in a way that is similar to the end of the world. If a gamma ray burst happens within 100 light years off the Earth, then it would be approximately 500 times brighter than the Sun and made in gamma rays. The energy sent to the high atmosphere of Earth would be the same as if 100,000 megatons of nuclear bombs went off. The ozone would be depleted. we'd have acid rain, but we'd also have flash burns, incineration of vegetation, perhaps something resembling nuclear weather. So many species could go extinct all over the world. Now, the other side of the Earth would be a special place to be because gamma rays don't go through the Earth, so you wouldn't get flash burned if you were there. However, the repercussions of altering the atmospheric composition and ozone depletion would ultimately come to the other side. And there nobody knows what will happen. This nightmare scenario has a 1 in a trillion probability of occurring once in Earth's history. It's going to be a nasty day if you get caught in the beam. For the reason that this is extremely powerful radiation, you don't want to be in the vicinity of this sort of energy, since it has the potential to break down your own molecules. Currently, there is no way to protect humanity against gamma-ray bursts that occur in close proximity to Earth. They move at the rate of 186,000 miles per second, or the speed of light. By the time we detected them, they would have already struck our planet. Gamma rays bursts could pose a hazard to the Earth, or to anything living that came within their born sight. Astronomers think that gamma ray bursts could be the cause of some mass extinctions on Earth. The one that happened 450 million years ago and killed off the Ordovician and Silurian species harder than those that lived deep in the ocean. This is consistent with what would happen during a strong gamma ray burst. In a galaxy the size of the Milky Way, gamma ray happen about once every few 100,000 years, according to astronomers. Even though they can be very bad, you have to be pretty close to be hurt by one. A gamma ray burst happens about once every 5 million years, which is close enough to affect life on Earth. In other words, since the Earth was made 4.6 billion years ago, there have been about 1,000 events. So the chances of a close gamma ray burst aren't zero, but they're low enough that you don't need to worry about them. Unless you want to live for about 5 million years. Humanity obviously made it through the gamma ray explosion unharmed, but this still demonstrates how far their effects may travel. Don't fret. Threats to Earth from gamma ray bursts are extremely low. All of the closest contenders for gamma ray bursts have been studied by astronomers, and none of them are either close enough or orientated in a way that would cause them to strike Earth. Therefore, what do you think? Imagine for a moment that 93 million miles away, a powerful force is brewing a force so intense that it has the potential to disrupt your daily life in ways you wouldn't expect. I'm talking about our very own sun, currently experiencing one of the most turbulent and awe-inspiring phases of its life cycle, the solar maximum. Right now, the sun is buzzing with activity, and its effects are being felt across the universe and even here on Earth. Why should you care? You might wonder, what does this fiery giant have to do with me? Well, a lot more than you think. Increased activity during this maximum doesn't just lead to beautiful auroras in the night sky. It can disrupt power grids, scramble your GPS, and interfere with radio communications. It's like an invisible storm raging across the cosmos, and it's influencing the technology we rely on every day. But to really grasp what's happening right now, we need to talk about the sun's 11-year cycle. Think of it as the sun's natural rhythm. It goes from quiet to chaotic, and back again over a period of 11 years. At the start of the cycle, things are calm. Fewer sunspots, fewer flares. But as we approach the solar maximum, all that changes. The sun becomes much more active, its surface crawling with sunspots, and bursts of energy explode in the form of solar flares. This is where we find ourselves now, right in the middle of this intense phase. Scientists from NASA and NOAA have confirmed that the sun is reaching its peak, and this solar maximum will continue for at least another year. So what does that mean for us? How does this massive ball of fire affect our modern world? And what can we expect as it continues to blaze with energy. Stay tuned as we dive into the fascinating world of the solar maximum, the science behind it, and why the sun is far more than just a bright light in the sky. Now let's really dig into what's happening during this solar maximum. What exactly is a solar maximum? Think of it as the sun's stormy season, but instead of rain and wind, the sun's magnetic field goes wild. During this phase, the sun's magnetic field becomes twisted and tangled, leading to the appearance of sunspots, those dark patches you might have seen in solar images. But don't be fooled by their appearance. These sunspots are cooler areas, but they are where all the solar action begins. When the sun's magnetic field lines cross or tangle too much, they snap, releasing massive bursts of energy called solar flares. These flares are so powerful they can shoot out waves of radiation and particles toward Earth at incredible speeds. And when those waves hit us, they can have a very real impact. How do scientists know this is happening? NASA and NOAA are constantly monitoring the sun with specialized satellites and observatories watching for these sunspots and solar flares. The latest data shows that we are smack in the middle of a solar maximum. Scientists measure the sun's activity by counting sunspots and tracking solar flare intensity. And right now, they're seeing an uptick in both. This heightened solar activity is all part of the sun's 11-year cycle, which shifts from quiet to chaotic. But don't worry, we're not talking about apocalyptic events. These are natural cycles that have been happening for millions of years, and they're crucial for understanding the sun's behavior and, by extension, the environment in space around Earth. What makes this solar maximum particularly interesting is that it's a little stronger than some scientists predicted. We're seeing more sunspots and stronger solar flares than expected, and that means the sun's magnetic field is even more twisted and dynamic than usual. But what does that mean for us? Let's talk about how this solar maximum affects you and me. When solar flares or coronal mass ejections, giant bubbles of solar plasma, reach Earth, they can disturb our planet's magnetic field, creating geomagnetic storms. These storms can have a few different effects. In extreme cases, a powerful solar storm can overload power grids, leading to blackouts. Solar flares can mess with the electronics on satellites, causing communication and navigation issues. Think GPS not working or your phone signal suddenly dropping. On the bright side, these solar storms can also trigger stunning displays of auroras, those glowing, colorful lights in the sky, also known as the northern and southern lights. So while the solar maximum brings some risks, it also delivers one of nature's most beautiful shows. And who doesn't love the idea of gazing up at a brilliant aurora, knowing it's a direct result of our sun's activity? Now that we understand the solar maximum, let's zoom in on two key players in this cosmic drama: sunspots and solar flares. Sunspots are cooler areas on the sun's surface, but they're anything but calm. They're actually where all the action begins. Think of them as the sun's storm clouds. Sunspots form because the sun's magnetic field is all twisted up, and where these magnetic field lines get really tight and intense, sunspots appear. What's fascinating is that these sunspots can be enormous. Some of them are even larger than Earth. As they increase in number during a solar maximum, scientists keep a close eye on them because they tell us how turbulent the sun's magnetic activity is getting. Sunspots are also the birthplace of solar flares. Picture a rubber band stretched to its limit. Eventually it snaps. That's what happens with the sun's magnetic field around sunspots. When the tension gets too high, the magnetic lines suddenly realign, and boom, a solar flare is born. Solar flares release enormous amounts of energy, equivalent to billions of nuclear bombs exploding at once. When a solar flare happens, it sends out intense bursts of radiation. Most of this radiation doesn't reach the surface of the Earth, but it can seriously disrupt our atmosphere. These flares can mess with satellite communications, knock out GPS systems, and even disrupt high-frequency radio signals. Imagine you're driving, relying on your GPS to navigate a busy city, and suddenly, no signal. That's a minor example of what a solar flare can do. For instance, in 1972, a solar flare knocked out long-distance telephone communication across several U.S. states. And while technology has advanced since then, we are even more dependent on satellites and electronics today, making us more vulnerable to these space weather events. Sometimes, along with solar flares, the sun also throws out huge clouds of plasma in what's known as a coronal mass ejection, or CME. These are the real heavy hitters of solar storms. If a CME is directed toward Earth, it can cause massive geomagnetic storms. When a CME reaches Earth, it can compress our planet's magnetic field and trigger geomagnetic storms. These storms can induce electric currents in power lines, potentially overloading transformers and causing widespread blackouts. One of the most famous examples is the 1989 Quebec blackout, where a geomagnetic storm caused a province-wide power outage. But CMEs don't just wreak havoc. They also create spectacular auroras. The particles from these solar storms interact with our atmosphere, lighting up the skies in vibrant greens, pinks, and purples. So while there's risk involved, there's also beauty in these cosmic phenomena. The more sunspots and solar flares we see, the more likely it is that one of these solar storms will hit Earth. That's why scientists are so interested in studying the solar maximum. They're not just observing for the sake of science. They're using this data to predict space weather and protect our technology. The better we understand these solar events, the better prepared we can be. Let's move beyond Earth for a moment and talk about space. During a solar maximum, the sun's increased activity doesn't just affect life down here. It poses a significant risk to astronauts and the technology we depend on in space. Imagine being an astronaut on the International Space Station ISS orbiting Earth as the sun throws out bursts of radiation. During a solar maximum, astronauts are at higher risk of exposure to dangerous levels of solar radiation. This can affect their health, causing radiation sickness, and even increase the risk of long-term problems like cancer. That's why space agencies like NASA have strict protocols during heightened solar activity. If a strong solar storm is on the way, astronauts might have to take shelter in specific areas of the ISS that are better shielded from radiation. Then we have satellites, those silent sentinels that orbit Earth, providing us with everything from GPS to satellite TV. During solar maximum solar flares and coronal mass ejections, CMEs can wreak havoc on these delicate instruments. You see, satellites are bombarded by charged particles from the sun, which can damage their electronics, causing them to malfunction or even fail altogether. One example of this happened in 1997, when a solar storm knocked out a major telecommunications satellite, causing issues with TV signals, credit card transactions, and even pagers back when we still used those. Today, we rely on satellites even more, and a similar event could have widespread consequences for communication and navigation systems. How do scientists protect against this? NASA, NOAA, and other space agencies monitor the sun's activity, closely tracking sunspots and solar flares in real time. They use this data to predict space weather and issue warnings when solar storms are coming. This allows engineers to put satellites in a kind of safe mode where they limit non-essential functions to protect sensitive electronics from being fried by solar radiation. Engineers also build shields into satellites to protect them from these radiation blasts. It's like giving our tech in space a layer of cosmic armor. But even with these precautions, solar storms are unpredictable, and the most powerful ones can still cause damage. Let's bring it all together. We've seen how the sun, in its solar maximum, can cause a cosmic storm affecting life on Earth, and even beyond, from disrupting power grids to threatening astronauts. But it's not just about the risks. It's also about learning and preparing for the future. The solar maximum will continue for another year or so, giving us a unique opportunity to study the sun during one of its most dynamic phases. And as we prepare for future missions to the Moon, Mars and beyond, learning about solar activity becomes even more crucial. The sun, once thought to be an unchanging ball of fire, is actually a living, breathing star with a profound impact on our lives. Remember, we're all connected to this massive star in ways both visible and invisible. Whether it's powering your GPS, dazzling you with northern lights, or sending a storm that shakes up space, the sun's cycles are a cosmic reminder of our place in the universe. Have you ever wondered, what if your life wasn't the only version of reality? What if somewhere out there there's another you living a completely different life, making different choices, following different dreams? Is this just a thought experiment, or could it be real? And if it is, how does that change everything we know about existence? In this journey, we'll dive into the science and philosophy of parallel universes, a concept so vast and mysterious that it might just redefine what we think reality is. Imagine this: somewhere far beyond the limits of our perception, there exists another version of you. Not just one, but countless versions. Perhaps in one reality, you're an artist creating breathtaking masterpieces, and in another, you're an explorer charting the unknown. It sounds like the stuff of science fiction, doesn't it? But what if it's more than just a story? What if the idea of parallel universes isn't fantasy, but a possibility rooted in the very fabric of our universe? For centuries, we've believed that reality is singular, one timeline, one set of events, one you. But the concept of parallel universes challenges that belief entirely. It suggests that reality isn't a single thread, but an endless web with infinite possibilities unfolding simultaneously. Think of flipping a coin heads or tails. Now imagine a world where both outcomes happen each in its own universe. It's hard to wrap our minds around, isn't it? But here's the real question. If these universes exist, where are they? Why can't we see them, touch them, or prove they're real? And if they are real, what does that mean for us, for our understanding of existence itself? It's a mind-bending idea, one that forces us to rethink everything we thought we knew about reality. And to truly explore its depth, we must turn to the science, where some of the most extraordinary theories suggest that parallel universes might be more than just a thought experiment. Parallel universes. What do we actually mean by that? Is it one big cosmic duplicate of our world, or something even stranger? The truth is, there's no single answer. Scientists and philosophers alike have explored multiple interpretations of what parallel universes might be, each more fascinating than the last. Let's start with one idea: infinite possibilities. Imagine every choice you've ever made, the roads you've taken, the words you've spoken. Now imagine every choice you didn't make, creating a new universe, a new reality, where things turned out differently. Perhaps in one universe you decided to pursue your childhood dream, and in another, you took a completely unexpected path. It's like a cosmic version of the choose-your-own-adventure story, where every option leads to a new chapter in an infinite book. Then there's the idea of alternate timelines. Think of history as a single thread running through time. Now imagine that at key moments, pivotal events in history, that thread branches out. What if, in another universe, dinosaurs never went extinct? Or if humanity never discovered fire? Entirely different timelines with outcomes we can't even begin to imagine might be unfolding alongside our own. But here's the twist. These interpretations aren't just philosophical musings. They arise from some of the most intriguing scientific theories. For example, quantum mechanics suggests that every quantum event could split reality into multiple outcomes. In one universe, a particle moves left. In another, it moves right. If you follow that idea to its logical conclusion, you end up with a vast, perhaps infinite multiverse, all springing from the fundamental unpredictability of the quantum world. And what about the cosmic scale? Some scientists propose that our universe is just one bubble in a vast cosmic foam, countless universes existing independently, each with its own set of physical laws. Imagine floating in an ocean where every bubble holds a completely different world. So whether it's infinite possibilities, alternate timelines, or entirely separate universes, the interpretations of parallel universes are as diverse as they are mind-bending. But one question remains: if these universes exist, is there any way we can connect with them, or even prove they're real? So if parallel universes exist, what does that mean for us? It's not just a scientific puzzle. It's a question that shakes the very foundation of how we see ourselves and our place in the cosmos. Let's start with the philosophical implications. If there are infinite versions of reality, then who are you really? Are you just one version of an infinite set of possibilities? It's a deeply unsettling idea. For centuries, philosophers have grappled with questions about identity, free will, and purpose. But the notion of parallel universes takes those questions to a whole new level. Think about it. In one universe, you might make a decision that leads to incredible success. In another, you might fail spectacularly. Does that mean your choices don't matter? Or does it mean every choice matters because each one creates a new reality? And then there's the question of fate and free will. If parallel universes exist, does that mean every possible version of your life is already out there, predetermined? Or are you still in control of your destiny, shaping one path while others unfold elsewhere? It's a paradox that challenges everything we think we know about how the universe works and how we work within it. Now let's shift gears to the scientific implications. The idea of parallel universes isn't just philosophical speculation. It emerges from some of the most cutting-edge theories in physics. For example, the many worlds interpretation of quantum mechanics suggests that every time a quantum event occurs, the universe splits into multiple versions. In one version, the particle moves left. In another, it moves right. This isn't just a thought experiment. It's a direct consequence of how quantum systems behave. And on a larger scale, there's the theory of cosmic inflation. According to this idea, our universe may be just one of countless others created during the rapid expansion of space after the Big Bang. Each universe could have its own unique physical laws, making our universe just a tiny speck in an unfathomably vast multiverse. But here's the kicker. If these parallel universes exist, how do we prove it? After all, they lie beyond the reach of our current technology and understanding. Yet scientists continue to search for clues, subtle hints in the cosmic microwave background patterns in the distribution of galaxies, or even phenomena we haven't yet discovered. So what does it mean to live in a universe where infinite possibilities exist, but we may never fully grasp them? Are we explorers of a vast unknown, or merely observers of a single narrow thread? The implications are as profound as they are mysterious, forcing us to rethink not just what we know, but how we know it. Now let's dig into the science, the hard evidence, and the theories that bring the idea of parallel universes out of the realm of imagination and into the world of physics. One of the most fascinating scientific ideas tied to parallel universes comes from quantum mechanics, the branch of physics that deals with the tiniest building blocks of reality, particles like electrons and photons. At this microscopic scale, the universe doesn't behave in ways we're used to. Instead of being predictable, particles exist in a strange state of uncertainty. Here's where it gets really interesting. In 1957, physicist Hugh Everett proposed a radical idea known as the many worlds interpretation. He suggested that whenever a quantum event occurs, whenever a particle has to choose between different states, the universe splits. Each possible outcome happens, but in a different branch of reality. Think of it like this. You're standing at a crossroads deciding whether to turn left or right. According to the many worlds interpretation, you turn left in one universe, and in another, you turn right. Both decisions are real, they just happen in separate realities. This theory isn't just about choices. It's about everything. Every quantum decision creates a branching network of parallel universes, each one following a different path. It's like an endlessly expanding tree, where every split creates new realities. But here's the catch. If these universes exist, we can't interact with them. They're separate like pages in a book that never overlap. This makes the many worlds interpretation both thrilling and frustrating. It offers a stunning explanation for quantum behavior, but leaves us questioning whether we'll ever know if these other worlds truly exist. Still, the theory has its supporters. Many physicists believe it solves some of the deepest mysteries of quantum mechanics. But it also raises profound questions about reality. If the universe is constantly splitting, then how do we define what's real? And if every possibility exists somewhere, does that mean nothing is truly unique, including you? The many worlds interpretation is just the beginning. To uncover even more about the science of parallel universes, we'll need to go beyond the quantum scale and into the vastness of the cosmos itself. If the many worlds interpretation explores the smallest scales of reality, cosmic inflation takes us to the largest, the very origins of the universe itself. This theory not only explains how our universe came to be, but it might also suggest the existence of countless others. So what is cosmic inflation? Imagine the universe as we know it, a vast expanse filled with galaxies, stars, and planets. Now rewind time. About 13.8 billion years ago, everything we see today was packed into an unimaginably small, hot, and dense point. Then in a fraction of a second, something extraordinary happened. The universe underwent a rapid, almost explosive expansion. This is what scientists call inflation. But here's where it gets fascinating. Many physicists believe that this process didn't just create our universe. Instead, inflation might have been happening everywhere, creating countless bubble-like universes, each expanding and evolving independently. Picture a pot of boiling water with bubbles forming, growing, and floating away. Each bubble is its own universe with its own unique physical properties and laws of nature. This means that our universe might be just one bubble in an endless multiverse, a vast cosmic foam where universes are born and die. And here's the truly mind-bending part. In some of these universes, the laws of physics could be completely different. Perhaps gravity is stronger. Maybe stars never form. Or maybe life evolves in ways we can't even imagine. The idea of a multiverse emerging from cosmic inflation isn't just theoretical. Some scientists are actively searching for evidence. For instance, if our universe ever collided with another distant past, it could leave subtle imprints in the cosmic microwave background, the faint glow of radiation left over from the Big Bang. But even without direct proof, cosmic inflation offers an elegant explanation for why our universe looks the way it does. Instead, we could be one of countless universes, each with its own story, its own reality. So what does this mean for us? If the multiverse exists, then everything we know, our galaxy, our planet, even ourselves, might be just one tiny piece of an incomprehensibly vast puzzle. And that's both humbling and exhilarating. But the search for evidence continues. Could we ever find direct proof of other universes? Or will they remain forever beyond our reach, hidden in the depths of an infinite multiverse? If parallel universes exist, how would we ever prove it? Scientists are exploring some of the most ancient clues in the cosmos remnants from the early universe itself to find answers. These observations might hold the key to unlocking the mystery of the multiverse. Let's start with the cosmic microwave background, or CMB. This faint glow of radiation is like a time capsule, a snapshot of the universe just 380,000 years after the Big Bang. It's the oldest light we can observe, and it holds a wealth of information about how our universe began. When scientists study the CMB, they look for patterns, subtle irregularities in this ancient light. These patterns tell us how matter was distributed in the early universe and how galaxies eventually formed. But here's the intriguing part. If our universe ever interacted with another universe, perhaps a neighboring bubble in the multiverse, it could have left a detectable mark in the CMB. Imagine two soap bubbles colliding. The point of contact creates a ripple. Similarly, a collision between universes might have left imprints in the fabric of space-time that we could still see today. So far, no conclusive evidence of such collisions has been found. But that hasn't stopped scientists from looking. Telescopes like the Planck satellite have mapped the CMB in exquisite detail, searching for anomalies that could hint at a multiverse. Another area of exploration comes from the distribution of matter in the universe. If parallel universes exist, they might subtly influence how galaxies are arranged on the largest scales. Some researchers have suggested that strange alignments or patterns in the cosmos could be the result of interactions with other universes. And then there's the concept of quantum fluctuations. These tiny variations in energy present during the inflationary period could have seeded the creation of not just galaxies, but entire universes. Observing these fluctuations and understanding their role might provide further clues about the multiverse. But here's the challenge: proving the existence of other universes is incredibly difficult. By definition, these universes exist outside our own, beyond the boundaries of what we can directly observe. It's like trying to see the other side of a wall when you're locked in a room. Still, the search continues. Scientists are pushing the limits of technology and theory, probing deeper into the origins of our universe. Every discovery brings us closer to understanding whether we're part of a multiverse or whether our universe stands alone in the vast expanse of reality. So could the answers be hidden in the light from the earliest moments of creation? Or will the multiverse remain forever, a tantalizing mystery, just out of reach? Now let's step away from the theories for a moment and dive into something more imaginative. What would it actually be like to live in a parallel universe? Could it feel similar to our own reality? Or would it be so different that we wouldn't even recognize it as life? Picture this. You wake up one morning in a parallel universe. At first glance, everything looks the same. The sky is blue, the trees sway in the wind, and the familiar buzz of life fills the air. But as you step outside, small details start to shift. Maybe the cars hover instead of drive. Perhaps the laws of physics allow people to float rather than walk. Or maybe history unfolded differently. Your city, your country, even your own life took a drastically different path. Now imagine another version, one where the differences are subtle. Maybe you're living the same life but with a few twists. You took a different career, married someone else, or pursued a long-forgotten dream. In a parallel universe, every decision, every chance encounter could lead to an entirely new reality. But what if the differences were more profound? In some universes, the laws of nature themselves could be entirely alien. Stars might never form. Planets might not exist. Time could flow backward, or gravity could be so weak that nothing holds together. Would such a universe even feel like reality to us? Here's a mind-bending thought. If we were to somehow find ourselves in a parallel universe, would we even know our senses and brains are adapted to perceive the reality we live in? A universe with radically different laws of nature might be completely incomprehensible, like trying to imagine a color you've never seen. But the biggest question is perhaps this: in a world of infinite possibilities, how much would those differences actually matter? Would you still be you in another universe? Or would the subtle changes in your environment, your choices and your circumstances create someone entirely new? Exploring what it's like to live in a parallel universe forces us to reflect on what defines reality and what defines us. Is it our surroundings, our experiences, or something deeper that transcends all possible worlds? And yet there's one more tantalizing question. If these universes are out there, could we ever visit them? Could we cross the boundaries of our reality and step into another? That's what we'll explore next. Now comes the big question. The one that feels like it's straight out of science fiction. Could we ever travel to other realities? Could we leave our universe and step into a parallel one? To answer that, we need to start by understanding the boundaries of our own universe. Right now, everything we know about space-time and matter suggests that our universe is a closed system. Like living inside a snow globe, we're confined to the dimensions and physical laws that define our reality. So the idea of breaking out and entering another universe seems impossible. But impossible is a word that science loves to challenge. Some theories suggest there might be loopholes in the fabric of space-time portals, if you will, that could allow travel between universes. Think of wormholes, those hypothetical tunnels connecting distant parts of space. Some scientists believe that if wormholes exist, they might also act as bridges between entirely different realities. Here's the catch. Wormholes, if they exist at all, would be incredibly unstable. The tiniest disturbance could cause them to collapse before anyone or anything could pass through. But what if we could stabilize one theoretically advanced civilizations far more advanced than ours might have the technology to harness wormholes as gateways to other universes? And then there's the idea of quantum entanglement, a strange phenomenon where two particles, no matter how far apart, are mysteriously connected. Some physicists speculate that this spooky action at a distance might hint at deeper connections between universes. Could quantum mechanics provide a roadmap for traveling between realities? Of course, there are massive challenges. Even if we discovered a way to reach another universe, we'd have no idea what conditions await us. Would it be safe? Would the laws of physics there even allow us to survive? Imagine stepping into a universe where gravity is so strong that you're instantly crushed, or so weak that atoms can't hold together. But there's another question, perhaps a more philosophical one. If we could travel to other realities, should we? What happens if we encounter another version of ourselves? What ethical dilemmas arise from meddling in a universe that isn't ours? For now, the idea of traveling to parallel universes remains a tantalizing dream, a frontier for future scientists and explorers to imagine. But even if we can't cross the boundaries of our reality, the very act of asking these questions pushes the limits of our understanding and inspires us to think beyond what we know. So will we ever build a bridge to another universe? Or will the multiverse remain forever out of reach, a world of infinite possibilities just beyond the edge of our imagination? Now let's confront one of the most profound questions about parallel universes. What happens if we interact with another version of ourselves? It's an idea that feels exciting and unsettling, all at once, raising ethical and philosophical dilemmas that challenge how we see ourselves and our place in reality. Imagine meeting another you. At first, it might feel like looking into a mirror, but this reflection isn't exact. Maybe they made different choices. Maybe they're living the life you always dreamed of or the one you've feared. How would that change the way you see yourself? Would you envy them, pity them, or would you feel a sense of connection knowing that their life could so easily have been yours? Here's the ethical dilemma. Would you have the right to influence their reality? If their life is better, would you try to learn from them or even take their place? If it's worse, would you feel obligated to help them, even if it meant disrupting their world? And what about the consequences of your interaction? Think about the ripple effect. In your universe, every choice you make affects the people around you. But in a parallel universe, the stakes could be even higher. A small action, one conversation, one decision might radically alter an entire timeline. Then there's the question of identity. If there are infinite versions of you, is there such a thing as the real? Are you defined by your choices, your circumstances, or something deeper, something constant across all realities? This isn't just a philosophical exercise. It's a question that strikes at the core of how we understand ourselves. And finally, the most unsettling question of all, what if the other version of you is fundamentally different? What if they've made choices that you can't reconcile with choices that challenge your sense of morality or identity? Could you still see them as you? Or would they feel like a stranger? Interacting with another version of ourselves isn't just a fascinating what if. It forces us to confront the nature of free will morality and selfhood. It's a thought experiment that asks if we are one of infinite possibilities, how much of who we are is truly unique. Perhaps the ultimate ethical question is this: if we ever had the chance to step into another version of our life, would we take it? Or would the risks to ourselves, to others, and to reality itself be too great? The idea of parallel universes isn't just a scientific or philosophical concept. It's a profound challenge to how we perceive reality and our place within it. For centuries, humanity has sought to understand the cosmos, from ancient myths about the heavens to the modern equations of physics. We've long assumed that our universe is all there is, that everything we know and experience exists within this singular reality. But the possibility of parallel universes forces us to confront an unsettling truth. What if we're just a tiny piece of something infinitely larger? Think about it. If there are countless other universes, each with its own stars, galaxies, and perhaps even life, then our universe, our home, might not be as unique as we once thought. That realization can feel humbling, even disorienting. Are we just one story among billions playing out in an endless cosmic library? And what about you? If infinite versions of you exist, each shaped by slightly different choices or circumstances, then what defines your individuality? Are you truly unique, or just one expression of endless possibilities? This idea doesn't just challenge how we see ourselves, it also forces us to rethink humanity's place in the grand scheme of things. For generations, we've seen ourselves as the center of the story, the observers of the universe. But if the multiverse exists, then we're not the center at all. We're a single thread in a vast, intricate tapestry, woven alongside infinite others. But here's the paradox. While the concept of parallel universes can make us feel small, it can also inspire a profound sense of connection. If reality is infinite, then every choice, every possibility, every moment has value. It's a reminder that even in the vastness of the cosmos, our actions still matter because they're part of something much greater than ourselves. The idea of parallel universes isn't just about what's out there, it's about how we understand our place in it. Are we explorers seeking answers to the ultimate mysteries? Or are we simply participants in a story so vast and complex that we may never fully comprehend it? Either way, it's a journey that forces us to see reality and ourselves in a whole new light. The concept of parallel universes doesn't just expand our view of the cosmos, it directly challenges some of our most deeply held beliefs about free will fate and the nature of consciousness. Let's start with free will. We like to think of our choices as defining who we are. Every decision, big or small, feels like a unique thread in the fabric of our lives. But what if in the multiverse, every choice you could possibly make does happen? In one universe, you chose one path. In another, a completely different one. If every possibility is realized somewhere, then do you truly have free will? Or are you just playing out one version of an endless set of possibilities? Then there's fate. If parallel universes exist, does that mean everything is inevitable? If every outcome exists in some reality, then does it matter which choices you make? Or does the existence of infinite possibilities mean that no single outcome is destined? It's a paradox that forces us to rethink what it means to be in control of our lives, and whether the idea of control itself even makes sense in a multiverse. And what about consciousness? Who are you in the context of infinite versions of yourself? Is your consciousness unique to this universe? Or is it somehow connected to all your counterparts in other realities? Philosophers and scientists have long debated whether consciousness is a purely physical phenomenon or something more profound. The multiverse takes this debate to a new level. Could our minds, our very sense of self, be just one fragment of a larger interconnected whole? Here's a thought experiment. If you could observe every version of yourself across all universes, would you still feel like the same person? Or would the differences, subtle or dramatic, redefine your understanding of who you are? The idea of parallel universes doesn't just stretch the boundaries of science. It forces us to confront some of the most profound questions about existence itself. It challenges the very concepts of individuality, choice, and identity, leaving us to wonder in a reality of infinite possibilities. What does it truly mean to be? These are not easy questions to answer, but they remind us that exploring the multiverse isn't just a journey through space and time. It's a journey into the depths of our own understanding, one that may forever change the way we see ourselves and the universe around us. Parallel universes don't just challenge our understanding of reality, they open the door to entirely new realms of discovery. If even a fraction of the multiverse theories prove true, they could revolutionize the way we see the cosmos and our place within it. Imagine the possibilities. If we could uncover evidence of other universes, we might learn why our universe has the specific properties it does, why the laws of physics are fine-tuned to allow stars to form, planets to exist, and life to evolve. Perhaps in studying other realities, we'd find universes where the conditions are wildly different, teaching us more about the delicate balance that makes our own universe so special. And what about the origins of reality itself? Parallel universes could provide clues about how and why the universe began. Some scientists propose that studying the multiverse might reveal whether the Big Bang was a singular event or just one of countless beginnings in an endless cycle of cosmic creation. Then there's the technological potential. If we could somehow harness the principles of parallel universes, like the mysterious connections hinted at by quantum mechanics, imagine what might be possible. Could we use those principles to solve problems we've never been able to solve before, like faster-than-light travel, infinite energy sources, or even new ways to explore the cosmos? But perhaps the greatest discoveries would come not from the differences between universes, but from what they share. By studying the multiverse, we might uncover universal truths, patterns, or principles that apply across every reality. These insights could help us better understand the deepest questions about existence, why there is something rather than nothing, what consciousness truly is, and what the ultimate fate of reality might be. Of course, these discoveries are still far off, lying on the very edges of what we can imagine. But the potential is breathtaking. The multiverse, if real, doesn't just expand the cosmos. It expands the boundaries of human knowledge, inviting us to explore not just the universe we live in, but the infinite possibilities that lie beyond. Ultimately, the pursuit of understanding parallel universes isn't just about science, it's about curiosity. It's about the human drive to seek answers to the biggest questions, to push past the limits of what we know, and to embrace the unknown with open minds and boundless wonder. The discoveries we make might not just change what we know about the universe, they might change what we know about ourselves. The possibility of parallel universes is more than just a scientific theory or a philosophical idea. It's an invitation to expand our imagination and challenge the way we see reality. Few concepts are as captivating or thought-provoking, drawing us into questions that seem to stretch beyond the limits of what we can understand. If these universes exist, they offer a glimpse into infinite possibilities, worlds where history unfolded differently, where the laws of physics may not resemble our own, or where versions of ourselves are living lives we can only dream of. But even if parallel universes remain forever out of reach, the very act of exploring them forces us to think bigger, to ask questions that transcend the boundaries of science and philosophy. At its core, the idea of parallel universes reminds us of the vastness of reality. It's humbling to imagine that our universe might be just one small piece of an endless multiverse, and yet it's exhilarating to know that we're part of something so immense, so mysterious, and so beautiful. And perhaps whether or not we ever find proof of other realities, the most important discovery might be what this exploration teaches us about ourselves, about our place in the cosmos, about the choices we make, and about the boundless curiosity that drives us to keep asking, keep searching, and keep wondering. So as we close this journey, consider this in a universe so full of mystery, where every possibility could exist somewhere. What does that mean for the choices you make today? What does it mean for how you see yourself, your world, and the infinite unknown? The answers may lie beyond our reach, but the questions will always push us forward. So as you step back into your own universe, carry this thought with you. Every question we ask, every possibility we imagine, brings us closer to understanding the extraordinary reality we call home. And who knows, perhaps somewhere in another reality, Another version of you is asking these very same questions, dreaming, exploring, and seeking answers in their own way. It's staring into the past, pulling up data that makes scientists question everything. Galaxies forming before they had time. Planets with chemicals that scream life. Structures too perfect for a chaotic cosmos. This isn't science fiction. It's real, measurable, and it's shaking our understanding to the core. The universe isn't playing by our playbook. It's showing us a cosmic puzzle, and the pieces don't fit. Webb's infrared eyes are catching things we can't ignore. From signals 124 light-years away to galaxies born when the universe was a baby. We're not just finding answers. We're finding questions we didn't know to ask. Today, we're diving into 4 discoveries that turn it all upside down. A planet with a gas that might mean life. A spiral galaxy that looks like home way too early. Auroras on Neptune that don't add up. And galaxies so old they break the timeline. This is the universe talking, and it's not whispering, it's shouting. Stick with us to see what Webb found and why it changes everything. What if a planet 124 light-years away is breathing? The James Webb Telescope found something on K2-18b that's hard to explain. K2-18b isn't just another dot in the sky. It's an exoplanet orbiting a dim red dwarf, sitting in the sweet spot where water could stay liquid. For years, it was just interesting. Too big to be like Earth, too far to make headlines. Then Webb turned its mirror, and everything changed. It scanned the planet's atmosphere, sifting light for chemical clues. What it found stopped scientists cold: dimethyl sulfide. On Earth, this gas comes from life. Tiny ocean creatures like plankton pump it out when they die. It's the smell of salty sea air, sharp and fleeting. Sunlight burns it away fast, so it needs constant replenishing. By life, Webb caught this signal in K2-18b's skies. Not a whisper, but a shout. The levels were high, way high. Think of it like spotting smoke from a fire across the galaxy. You don't know what's burning, but something's alive. This planet has a thick, hydrogen-rich atmosphere, probably cloaking a deep ocean. If life's there, it's not fish or forests. Maybe microbes floating in that alien sea churning chemicals, or something we can't even picture. The signal's strong enough to suggest more than a few specks. It could be an ecosystem, a living world pumping gas on a massive scale. But hold on, science doesn't jump to aliens. There's a catch. Other chemicals like methane can mimic this signal in infrared. Mistakes happen, so they checked again. The signal didn't fade. It got clearer. Stronger, estimated at 1,000 times Earth's levels. That's not a glitch. That's something real. Now, could it be geology, a weird volcano, or gas pocket? Maybe. But on Earth, nothing non-living makes dimethyl sulfide like this. We've looked. No dice. If K2-18b's doing it without life, we need a new rulebook. This is where the cosmic puzzle gets wild. K2-18b isn't some distant theory. It's 124 light-years away, close enough to study, far enough to haunt us. If this is life, we're not talking fossils or dreams. We're talking something alive right now, leaving its mark in the sky. Webb's data is solid, but it's not the final word. More checks are coming. Other telescopes, other teams. They'll rule out every trick, every false alarm. Chemistry, physics. If nothing else fits, we're left with one answer: life. That changes everything. We're not just asking if we're alone. We're measuring what else is out there. What's its chemistry? How does it survive? Is it like us or something stranger? K2-18b's signal is a piece of the puzzle, and it's screaming for attention. We used to think alien life was a future problem, something for starships or science fiction. But now it might be staring us down. A signal from a planet we can almost touch. This isn't the end of the story. It's the start. K2-18b's signal hints at life. But what if the universe built galaxies too perfect for its own rules? What if a galaxy looked like home, but showed up billions of years too early? Webb found one, and it's turning our timeline upside down. Meet Zulong, or Torch Dragon, a spiral galaxy spotted by the James Webb Telescope. It's not just far away. It's far back, shining from when the universe was barely 1 billion years old. That's not long after the Big Bang, when everything was supposed to be a mess. Picture the early cosmos like a stormy sea with gas and stars crashing, merging, tearing apart. Galaxies back then should be chaotic blobs, not orderly spirals like our Milky Way. Spirals need time. Time for gravity to settle, for stars to align into neat arms, for a disk to spin steady. That takes billions of years, or so we thought. Zhulong breaks the rules. It's got those arms that balance that structure. It looks like it's been chilling for ages, not freshly born in a cosmic riot. Think of it like finding a polished statue in a quarry where rocks are still being blasted. It shouldn't be there, but Webb's infrared eyes caught it clear as day. The light we're seeing left Zhulong when the universe was a toddler, yet it's already grown up. Its spiral arms are tight, its core is bright, and it's stable. That means it formed even earlier, maybe just a few 100 million years after the Big Bang. Here's the science. We measure this distance with redshift. It's how light stretches as the universe expands, pushing starlight to redder colors. Zhulong's redshift puts it at 12.5 billion years away. That's not just a number, it's a problem. Our models say spirals come late after messy galaxies collide and cool. Zhulong says otherwise. It's not alone either. Webb's finding more like it, galaxies too neat for their time. This is another piece of the cosmic puzzle, and it's not fitting. Why does this matter? If spirals formed this fast, the universe was cooking way sooner than we thought. Maybe gravity worked harder back then. Maybe dark matter, that invisible glue, pulled stars together like a magnet on steroids. Or maybe our whole timeline's off. Some scientists are rethinking how gas clumped in the early days. Others wonder if the first stars burned out faster, spitting out material for galaxies like Zhulong. The wilder idea: the universe's rules might have been different back then. Not by much, but enough to rush things. This isn't just about one galaxy. It's about what's possible. Spirals like Zhulong are stable. They're the kind of places where stars last, where planets form, where life might get a shot. If they were around this early, life-friendly spots could have popped up way before we expected. That's big. It means our Milky Way, our home, isn't so special. It's just one of many, maybe late to the party. Zhulong's telling us the universe didn't waste time. It was building homes while we thought it was still setting up shop. Webb's not done. It keeps spotting these early spirals, each one a jab at what we thought we knew. Zhulong's not an outlier. It's a clue. A clue that the cosmic puzzle has more pieces than we guessed. We're not just looking at a galaxy, we're looking at a universe that's been ahead of us from the start. And that's what makes this so unsettling. The past looks too much like now. Zhulong's early spiral defies the stars, but what's hiding closer in our own cosmic backyard? The James Webb Telescope turned to Neptune, and it's not what we expected. Neptune's the loner of our solar system. Far out, cold, dark, and barely studied. Most of what we know comes from one quick visit by Voyager 2 in 1989. Since then, it's been blurry glimpses through ground telescopes. Nobody thought to point Webb, our deep space champion, at a planet next door. But they did. And what it saw wasn't just pretty lights. It was a puzzle piece that doesn't fit. Webb caught Neptune's auroras glowing at its poles. Not like Earth's northern lights, all soft and shimmery. These are wild, chaotic, driven by forces we don't fully get. Think of it like finding a strange signal on a radio you thought was broken. Something's broadcasting and it's loud. Webb's infrared vision cut through Neptune's haze, mapping heat and chemistry in ways we've never seen. It spotted auroras pulsing with weird patterns, hot spots where there shouldn't be heat, cold patches that defy the sun's weak grip out there. On Earth, auroras come from solar wind-charged particles slamming into our magnetic field. Neptune's got a field too, but it's a mess. Tilted, lopsided, nothing like ours. Those particles take forever to reach it, crawling through space from the sun. Yet Webb saw something else. Temperature swings that don't add up. Some areas cooled too fast. Others burned hotter than they should. It's like Neptune's cooking its own weather and we don't know the recipe. Here's the data. Webb's instruments tuned for distant galaxies picked up chemical shifts in Neptune's atmosphere. Methane absorbs light in weird ways, but something's tweaking it. Maybe magnetic storms. Maybe reactions we haven't pinned down. The auroras aren't just a light show. They're clues to a planet we thought we knew. Neptune's magnetic field is a beast twisting in ways that mess with our models. Those hotspots could be energy leaking from inside the planet. Those cold zones, maybe gas sinking in ways we didn't expect. We're not sure. And that's the point. Webb didn't just snap a picture. It raised questions we weren't asking. This isn't about some far-off star. It's right here in our own system. Neptune's been out there keeping quiet while we chased galaxies. Now Webb's showing us we missed something. The sample mentioned Voyager's flyby, but Webb's look is sharper, deeper. It's not just auroras. It's a planet acting alive with storms and heat and chemistry that don't play by our rules. And it's not alone. Uranus-Neptune's twin might be hiding similar tricks. We haven't looked hard enough. Our outer planets are strangers, and Webb's proving it. Why does this matter? It's another crack in the cosmic puzzle. We thought we had our solar system figured out. Earth, Mars, Jupiter done. But Neptune's saying, hold up. There's more. Its auroras hint at forces magnetic, chemical, maybe even geological, that could teach us how planets work. Not just here, but everywhere. If we're wrong about Neptune, what else are we missing? Moons with oceans. Weather we can't predict. This isn't just a pretty view. It's a wake-up call. The universe doesn't stop surprising us even in our own backyard. Webb's not done with Neptune. More observations are coming. Maybe they'll crack the code on those auroras, or maybe they'll dig up new mysteries. Either way, this telescope's rewriting what we thought was settled. It's telling us to look closer, even at the places we thought we knew. Neptune's auroras aren't just lights. They're a signal. Something's going on out there and we're just starting to listen. Neptune's auroras glow with secrets. But what if galaxies, if they were allowed? The James Webb Telescope found some, and they're breaking every rule. Say hello to JD's GS Z14-0. It's not just a galaxy, it's a time bomb. Webb spotted it shining when the universe was only 280 million years old. Back then, the cosmos was a hot mess. Gas, swirling stars, barely sparking matter, still figuring itself out. Galaxies weren't supposed to happen yet. They need time. Time for gas to cool, for stars to clump, for gravity to sculpt something solid. Picture it like trying to bake a cake in a microwave that's still warming up. You shouldn't get a cake. But JD's GS Z14-0 is no raw batter. It's a full-on galaxy, compact, bright, packed with millions of stars. This is nuts. Our models said galaxies take billions of years to get their act together. First you need stars, tiny ones made of hydrogen and helium burning fast and dying young. They explode, spitting out heavier stuff like carbon. That stuff cools, collapses, forms new stars, and slowly builds galaxies. JD's GS Z14-0 laughs at that. It's got structure, mass, and shine all before the universe even had a chance to stretch its legs. Think of it like finding a skyscraper built before the invention of steel. Webb's got the receipts. It measures this with redshift. JD's GS Z14-0's redshift screams 13.5 billion years old. That's not just far, it's impossible. Or it was. This galaxy's got a mass of 100 million suns squeezed into 500 light-years. It's small but mighty, and it's not alone. Webb's finding more like it galaxies popping up way too early, too bright, too big. This is where the cosmic puzzle cracks open. Something sped things up. Maybe dark matter, that invisible scaffolding, yanked matter together like a cosmic tow truck. Maybe the first stars were giants blowing up fast and seeding galaxies in a hurry. Or maybe the universe's early rules were looser, gravity stronger, time weirder. Scientists are scrambling. Some say gas clouds collapsed faster than we thought. Others think dark matter played a bigger role. The wild ones, they're whispering about new physics stuff we haven't dreamed up yet. Why is this a big deal? These early galaxies aren't just old, they're game changers. If they formed this fast, the universe was ready for business way sooner than we planned. Stable galaxies mean stable stars. Stable stars mean planets. Planets mean chances for life way back when we thought the cosmos was still in diapers. JD's GS Z14-0 isn't just a pretty dot. It's a clue that the universe didn't wait around. It was building fast while we were busy writing rules it doesn't follow. Webb's stacking up these finds, more early galaxies, each one a jab at our timeline. They're not flukes, they're a pattern. The cosmic puzzle keeps growing, and this piece is heavy. It's telling us the universe was never slow. It was always in a rush, spinning out galaxies like it had somewhere to be. And that's what's spooky. We thought we knew the story of the cosmos. But JADIS GS Z140 says we're reading the wrong book. Webb's not just showing us stars, it's showing us how much we've got to learn. Early galaxies flipped the script. But what does it all mean for us? The James Webb telescopes rewriting our place in the cosmos. Look at what we found. K218b's got a gas that might mean life pumping out signals we can't ignore. J-Long's spiral showed up way too early, looking like home, before it should. Neptune's auroras are dancing with secrets right in our backyard. And JADIS GS Z140, that galaxy born too soon, says the universe was in a hurry. These aren't just dots in the sky. They're pieces of a cosmic puzzle, and they're telling us something big. The universe isn't what we thought. It's not slow, not empty, not quiet. It's been busy building galaxies, maybe even life, long before we had a clue. This changes the game. We used to ask if we're alone. Now we're asking how many others are out there. Are we just one piece in a massive puzzle or something special? Webb's data doesn't shout answers. It whispers hints. Galaxies too old. Signals too strong. Lights too weird. Each one's a crack in what we thought we knew. And it's not over. More discoveries are coming. More questions. More pieces. So what now? Keep looking up. The universe is talking, and we're finally listening. Not with dreams, but with hard data. Webb's showing us a cosmos that's alive, restless, and full of surprises. Are we ready to find out what's next? The puzzle's not solved. It's just getting started. Welcome to our journey into the dark and mysterious world of black holes. The enigmatic powerhouses of the cosmos. Black holes, regions in space where gravity pulls so strongly that not even light can escape, have intrigued scientists and the public alike for decades. In this video, we'll explore what black holes are, how they form, and why they are crucial in understanding the universe. Join us as we dive deep into the science of black holes, uncovering their secrets and the groundbreaking methods used to study them. What is a black hole? A black hole forms when a massive star collapses under its own gravity at the end of its life cycle, squeezing all of its mass into an infinitely small point known as a singularity. Surrounding the singularity is the event horizon, often described as the point of no return. Once anything crosses this boundary, escaping the black hole's gravitational grip becomes impossible. Black holes come with fascinating properties. Firstly, their mass, which can be several times that of our sun, or as massive as millions of suns, when we talk about supermassive black holes at the centers of galaxies. They might also possess spin, rotating at immense speeds and influencing everything in their cosmic neighborhood by twisting space-time itself. Despite their dark nature, black holes are not just cosmic vacuum cleaners. They play a crucial role in the structure and evolution of galaxies, including our own Milky Way. Understanding these mysterious objects not only answers questions about the universe, but also about the fundamental laws of physics. The formation of black holes is a dramatic process, usually stemming from the remnants of a large star that has ended its life in a spectacular supernova explosion. Let's delve into how these mysterious objects come into existence. When a star significantly larger than our Sun exhausts its nuclear fuel, it undergoes a dramatic transformation. Without the outward pressure generated by nuclear fusion to counteract gravity, the star collapses under its own immense gravitational pull. This collapse triggers a supernova, an explosion that outshines entire galaxies and ejects matter into space. For the most massive stars, what remains after this explosion is a core so dense that no known physical forces can stop its collapse, leading to the formation of a black hole. The core effectively collapses to a point of infinite density, a singularity where the laws of physics as we know them no longer seem to apply. But supernova remnants are not the only way black holes can form. In the vast expanse of the universe, black holes can also result from the direct collapse of massive gas clouds under certain conditions, skipping the star phase entirely. This process is thought to contribute to the formation of the supermassive black holes found at the centers of most galaxies, including our own Milky Way. Additionally, when black holes merge, a phenomenon observed through the detection of gravitational waves, they can form larger black holes, further adding to the diversity of these objects in the cosmos. In essence, black holes are born from the death of stars and other high-mass entities, playing a critical role in the cosmic cycle of matter and energy transformation. The detection of black holes. Detecting black holes is a complex task due to their invisible nature. Since no light can escape from them, astronomers must rely on indirect methods to prove their existence and study their properties. One primary method of detecting black holes is through their interaction with nearby matter. In binary systems, where a black hole is paired with a normal star, the black hole can pull in material from its companion. This material forms an accretion disk around the black hole, heating up due to intense gravitational forces and emitting high-energy X-rays before disappearing into the black hole. These X-rays, which can be detected by space-based telescopes, are a telltale sign of the presence of a black hole. Another method involves observing the orbits of stars around an invisible object. In the heart of our Milky Way galaxy, for example, astronomers have charted the orbits of stars around a region called Sagittarius A. The movement of these stars indicates they are orbiting a massive invisible object, confirmed to be a supermassive black hole. Gravitational lensing is also a powerful tool for detecting black holes. This phenomenon occurs when a black hole bends the light from a background object, such as a galaxy or star, due to its extreme gravitational field. This bending causes the light to distort and magnify, appearing as rings or arcs from our viewpoint on Earth. The most recent and groundbreaking method is the detection of gravitational waves, ripples in spacetime caused by some of the most violent and energetic processes in the universe. When two black holes spiral around each other and eventually merge, they emit these waves, which can be detected by facilities like LIGO and Virgo. These observations provide direct evidence of black holes and allow scientists to estimate their masses and other properties. Through these methods, astronomers continue to enhance our understanding of black holes, shedding light on some of the most mysterious objects in the cosmos. Black holes and relativity. Black holes are not only fascinating celestial phenomena, but also crucial elements in the study of Einstein's theory of general relativity. This theory, which revolutionized our understanding of how gravity works, predicts that massive objects can warp the fabric of spacetime, and black holes are extreme examples of this effect. At the core of general relativity is the concept that gravity is not a conventional force, but a curvature of spacetime caused by mass and energy. Black holes, with their immense mass concentrated into an infinitely small point, create profound distortions in spacetime. This is why near a black hole time seems to slow down, and the paths of light and matter are bent, a phenomenon known as gravitational lensing. The Schwarzschild radius, or the event horizon of a black hole, is a direct consequence of relativity. It defines the boundary around the singularity, where the escape velocity equals the speed of light. According to relativity, nothing inside this radius can escape the black hole's gravitational pull, making the event horizon a perfect one-way exit from our observable universe. Black holes also challenge our understanding of spacetime through their singularities points, where the curvatures of spacetime become infinite. The laws of physics as we know them break down at these singularities, posing significant theoretical challenges and pushing scientists to think about quantum mechanics and gravity in new ways. Observations of black holes thus provide critical tests for the theory of general relativity. Events like the recent imaging of a black hole's shadow by the Event Horizon Telescope and detections of gravitational waves from black hole mergers offer unprecedented insights. These observations not only support the predictions of relativity, but also open new avenues for understanding the fundamental laws that govern our universe. Through their extreme nature, black holes serve as natural laboratories for testing ideas about gravity spacetime and the limits of our physical laws, making them indispensable to the field of theoretical physics. Famous black holes and discoveries. Black holes might seem like uniform entities, but they are as varied as the cosmic phenomena that surround them. Some of the most notable black holes have unique stories that have significantly contributed to our understanding of the universe. Cygnus X1. One of the first black holes ever identified, Cygnus X1, became a key subject in the study of these cosmic objects. Discovered in the 1960s as a strong X-ray source, it was later confirmed to be a black hole through its interaction with a companion star. Observations of matter being pulled from the star into Cygnus X1's accretion disk helped astronomers validate the existence of black holes and provided a laboratory for studying extreme gravitational effects. Sagittarius A. At the center of our Milky Way galaxy lies Sagittarius A, a supermassive black hole with about 4 million times the mass of the Sun. Its presence was deduced from the orbits of stars at the galactic center, with their speeds and paths suggesting an extremely massive, invisible object. Sagittarius offers a closer look at the dynamics of black holes at the centers of galaxies and their interactions with nearby stars and gas. M87. The black hole at the center of the M87 galaxy made headlines in 2019 when the Event Horizon Telescope captured the first ever image of a black hole's event horizon, or its shadow. This remarkable achievement not only provided visual evidence of black holes, but also confirmed general relativity's predictions at the edges of one of the most extreme environments in the cosmos. Gravitational wave discoveries. The LIGO and Virgo observatories have detected gravitational waves from several black hole mergers since 2015. These detections are crucial as they provide a new way of observing black holes and testing the limits of our physical theories. Each merger helps astronomers learn more about black hole masses, spins, and the history of galaxies. These iconic black holes and their studies have opened new windows into the high-energy universe, providing crucial insights into gravity spacetime and the ultimate fate of massive stars. Unanswered questions and future research. Despite significant advancements in our understanding of black holes, they continue to be sources of profound mysteries and the subject of intense scientific inquiry. Here are some of the unanswered questions and the future research paths that scientists are pursuing to unravel these enigmas. Inside the event horizon, what happens inside a black hole remains one of the biggest questions in physics. Theories suggest that within the event horizon lies the singularity, a point where space and time cease to exist as we know them and where the laws of physics break down. However, the true nature of singularities and what happens to matter as it approaches this point is still speculative. Understanding this could lead to breakthroughs in our comprehension of gravity and quantum mechanics. Information paradox. The black hole. Information paradox poses a significant challenge to theoretical physics. It arises from the contradiction between quantum mechanics, which suggests information is never lost, and general relativity, which implies that information can disappear in a black hole. Resolving this paradox is crucial for a unified theory of quantum gravity, and research in this area is vigorous with concepts like Hawking radiation and firewall hypotheses being explored. Formation and growth of supermassive black holes. The origins and rapid growth of supermassive black holes, especially shortly after the Big Bang, remain unclear. These black holes are millions to billions of times the mass of the Sun and are found at the centers of most large galaxies. Understanding how they formed and grew so massive in a relatively short period of cosmic history is critical for piecing together the evolutionary puzzle of the universe. Future missions and observations. Upcoming missions and observatories promise to shed more light on black holes. The Event Horizon telescope continues to refine its observations to produce more images of black holes. Space missions like the James Webb Space Telescope and the planned Laser Interferometer Space Antenna LISA will explore the early universe and detect gravitational waves from black hole mergers across vast distances, offering new insights into their properties and behavior. Through these and other research initiatives, scientists continue to explore the enigmatic nature of black holes, pushing the boundaries of our knowledge and technology to solve the cosmos's most compelling mysteries. Thank you for joining us on this fascinating journey through the mysterious and powerful realms of black holes. We hope this exploration has sparked your curiosity and expanded your understanding of these cosmic giants. If you enjoyed this video and would like to dive deeper into the wonders of the universe, don't forget to hit the like button and subscribe to our channel for more engaging science content. Your support helps us bring more exciting topics to light. Have any thoughts or questions about black holes? Or is there another cosmic phenomenon you're eager to learn about? Let us know in the comments below. We love hearing from you and are always looking to tailor our content to what you're most curious about. Remember, the universe is vast and full of wonders waiting to be discovered. Stay curious, keep exploring, and until next time, keep looking up. Some stars are so massive, so luminous, they could swallow our entire solar system and still have room to breathe. Tonight, you'll drift past them, not as an observer, but as a traveler. These are the behemoths, cosmic titans that live fast, burn furiously, and explode with enough energy to shape galaxies. And somewhere in their death is the reason you exist. And some of these stars, they're colossal. If seen clearly, one would engulf Mercury, Venus, Earth, and even Mars. These are the titans you came to meet. Despite their grandeur, these giants are fleeting. They live fast and die spectacularly, returning their matter to the universe that gave birth to them. As you drift closer, you begin to understand they are not just fascinating, they are foundational. Without them, you wouldn't be here. Their collapse forged the elements in your bones, your blood, the air you breathe. You are quite literally made of star stuff. So before you settle in, if journeys like this mean something to you, consider liking the video and subscribing, but only if you genuinely enjoy this kind of voyage. And I'd love to know, where are you watching from? And what time is it right now? Now, dim the lights. Maybe turn on a fan for that soft hum, and let's begin tonight's journey. You start in a quiet corner of our galaxy, near the local neighborhood of stars. Through the lens of space, even nearby suns seem faint. Their light has traveled for years to reach you, moving at nearly 300,000 kilometers per second. Out here, distance is time. 1 year of light travel equals nearly 10 trillion kilometers. It's a number so large, it slips away from grasp. So when you gaze at UY Scuti, the giant star we'll meet tonight, you're seeing it not as it is, but as it was, almost 10,000 years ago. And when you arrive at its doorstep, what greets you isn't fire. It's haze, a deep red fog, like a slow breath, exhaled by the universe itself. The star is old, massive, a red supergiant that once blazed blue in its youth. Over millions of years, it swelled outward, its core still fusing elements in violent heat. Hydrogen to helium, helium to carbon, carbon to oxygen. Like layers in a cosmic oven, its surface isn't solid, but roils with convective gas. Bubbles the size of planets rise and fall. Like boiling water, the outer layers are barely held together. Gravity and radiation, locked in a fragile, flickering dance. Even from millions of kilometers away, the heat would unmake you. And yet, you feel calm, small, in the best possible way. Not diminished, but placed in scale. A quiet thought passes through. How many of these giants float in the Milky Way alone? Tens of thousands, maybe more, most hidden behind dust and silence. Even now, drifting near UY Scuti, you see the night isn't black, it's velvet, deep, laced with soft radiation, the afterglow of ancient energy, cosmic microwave background, ionized hydrogen, light from galaxies too far to resolve. Some astronomers still debate whether UY Scuti is truly the largest. Stellar measurements are delicate. Dust mass loss and distance skew the numbers, but that's not what matters. What matters is this: you're floating beside a thing so vast, even your imagination struggles to grasp it. And this is only the beginning. Ahead, more giants await. You begin to understand how far and how bright these behemoths shine across interstellar space. You drift slowly as if weightless on a current of thought and photons. The distances between stars stretch like taffy pulled across eons. There are no hard lines in space, only gradients between heat and cold light and shadow time and timelessness. Light, the quiet courier of space, is your guide. It reveals not only where a star is, but when it was. This simple idea becomes profound out here. To look at the stars is to peer into the past. Every twinkle you remember seeing from Earth is ancient. Even the nearby Alpha Centauri system is more than 4 years gone by the time its light touches your eye. For behemoth stars, this becomes even more powerful. Their light can stretch across entire galaxies, even briefly outshining all the other stars combined. These are luminous giants, massive bodies whose brilliance is not merely for show, but a byproduct of immense energy and violent fusion. And yet, even the brightest among them are dwarfed by the scale of interstellar space. Light moves fast, but the cosmos expands faster still. You float past a point where the light from one star, one magnificent swollen supergiant, has been traveling for 10,000 years and is just now passing by your invisible shoulder. The brightness of a star isn't just about its actual power. It's about perspective, its luminosity, versus its apparent brightness. A nearby candle can outshine a distant bonfire. But astronomers have learned to disentangle this illusion using the inverse square law of light. Each doubling of distance makes the light appear 4 times dimmer. So when you see a star like R136A1 burning at its core with temperatures over 50,000 Kelvin, you know it must be truly luminous to appear as bright as it does from Earth. Another star, Deneb, a blue-white supergiant in Cygnus, is so bright it rivals other nearby stars. Even though it's nearly 2,600 light-years away, its light left around the time ancient Mesopotamians were building ziggurats. And only now it reaches us, quietly, consistently. A reminder that space is not empty. It is full of stories told in photons. You imagine yourself traveling at the speed of light. Even then you realize it would take years to traverse just this quiet arm of the galaxy. Across the Milky Way, over 100,000 years. And yet light makes this journey, every second, without fatigue. No vessel, no engine, just momentum and time. And as you float, you start to sense a subtle truth. That starlight is the language of the cosmos. Every wavelength carries a message, a temperature, a speed, a chemical signature. And like a quiet archivist, the universe records its story, in spectra. One such story lies ahead. You notice it even now before you reach it, a faint crimson halo on the edge of darkness. The telltale glow of hydrogen alpha emissions filtered through interstellar dust. It marks the domain of another giant. You slow your pace, not from fear but from reverence. Because the star ahead, Stephenson 218, exists at the very boundary of known stellar dimensions. Some models suggest its radius is over 2,100 times that of the Sun. If placed in our solar system, its edge would stretch past the orbit of Saturn. And yet, you could fly past it and never truly see it, because it is cloaked, hidden, a ghost, in the haze. Before you approach your thoughts, linger on the scale of this moment. You've traveled dozens behind. There's a subtle ache in this realization. That brilliance doesn't last, that the most powerful lights fade fastest. And yet, that too is natural. That too is beautiful. Some astronomers believe the upper limit of stellar size is still not well understood. We can model fusion and gravitational balance, but turbulence, magnetic fields, and stellar winds complicate the math. Observations help, but stars like Stephenson 218 lie buried behind veils of interstellar gas, visible only in slivers of infrared and radio data. Some question its precise size. Some argue it could be a cluster, but for now, it holds a kind of quiet throne in our records. A record, not of ego, but of scale. As you prepare to approach, the light grows redder, deeper. Dust scatters short wavelengths, letting only the longest, warmest reds pass through. It's like drifting into a sunset that never ends. And even now, space holds its silence. No roar of fusion, no flicker of noise, just starlight, stretching into forever. You encounter Ui Scuti, an immense red supergiant near the edge of known stellar scale. You arrive without a sound, slipping into the quiet reach of Ui Scuti's domain. There is no firm edge to cross, only a gradual swelling of light and warmth, thick as breath. You hover now near one of the largest stars ever measured by volume, a red supergiant residing in the constellation Scutum, about 9,500 light-years from Earth. The star is not bright in the visible sense. Its energy is stretched and spread, softened by the sheer distance, and by the dust that floats between galaxies like fine smoke. What you see is not blinding, but warm. It glows in the deep red and infrared parts of the spectrum, casting a long, lazy light across the emptiness. Ui Scuti is a strange place to imagine. A single object, and yet its surface would engulf the orbits of Mercury, Venus, Earth, and Mars. Light takes more than 7 hours just to travel from one side of it to the other. And yet it is not a solid thing, not even a clearly defined one. Its edges blur into the vacuum. Its atmosphere is a dance of heated gas, always rising, falling, and leaking away into space. Inside the vast convective layers of this star, pressure and temperature are constantly fighting gravity's slow pull. The outer layers swell because the radiation generated deep in the core is strong enough to push them outward. And in doing so, the star becomes fragile, unstable. Its surface is not uniform, but pocked with great cells of gas. Some astronomers believe a single one of these bubbles, convective cells, can be larger than Earth's entire orbit. At the center of this expanding colossus, fusion still occurs. Hydrogen has long been depleted, and helium is now fusing into heavier elements, carbon, oxygen, magnesium. This is a critical phase. The star is nearing its end. Once the core becomes too heavy to resist collapse, iron will form, and iron is the great boundary in stellar physics. Fusion of iron doesn't release energy, it absorbs it. When that moment comes, the balance shatters, and the star will implode. But that is still in the future. For now, UY Scuti pulses slowly, like a cosmic heartbeat. It is classified as a pulsating variable star, its brightness shifting as its outer layers expand and contract. This breathing cycle is slow months long and gives the star its rhythm, like the tide. From your vantage point, you observe another peculiarity. UY Scuti is losing mass. Its outer layers drift away, carried off by stellar winds, streams of particles blown by radiation pressure. Over time, this process peels the star apart. It's one of the reasons astronomers debate its actual size. Because the outer envelope is so diffuse, it's hard to say where the star truly ends. You reflect for a moment on how little of this was known just decades ago. In the 20th century, red supergiants were assumed to be rare, mysterious anomalies. Only with the rise of space telescopes and precise spectroscopic methods did we begin to map their true dimensions. And even now, some data is debated. Distance estimates, mass loss rates, temperature fluctuations. But uncertainty doesn't dim the wonder, it expands it. Some researchers propose that UY Scuti may shrink as it evolves, its mass loss and internal changes gradually collapsing it into a hotter, smaller star before the final supernova. Others believe it may be on the brink already, that its next contraction could be the last. The supernova of a star like this would not just be bright, it would be transformative, a release of energy so vast it could outshine an entire galaxy for weeks. Neutrinos would flood space. Elements like gold, platinum, and uranium would be born in that furnace. This is cosmic alchemy, stars turning themselves inside out, to seed the universe with complexity. But tonight, that moment is not here yet. Tonight you float beside a star so large, your mind falters at the scale. The texture of it, the slowness of its surface, the quiet distance of its core. You feel as though you are orbiting a whole world, not a single star. And still, even in this enormity, UY Scuti is not alone. Other giants await, some even larger, some far more massive. You begin to pull away, your thoughts still trailing behind. The red light lingers in your vision, like the afterglow of a dream. Ahead, space is darker again, but not empty. In the far silence, another giant pulses. This one, less known, more obscure, but perhaps even larger. Its name is whispered among catalogs and in quiet debates. Stevenson 218. You turn toward it, letting the light of UY Scuti fade gently behind you, and begin the slow glide, deeper into the realm of hypergiants. You learn why some stars are larger, others heavier, and how this affects their fate. As you drift onward, the red glow of UY Scuti dissolves behind you, like a sunset slipping below the edge of time. Ahead, space stretches wide and cool, a canvas of subtle light and gravitational tension. You move through stillness, but the physics beneath that stillness hums with complexity. Out here, size is not always what it seems. One star might swell to the edge of Saturn's orbit, yet possess only a fraction of the mass of another, smaller, hotter star. In astronomy, the distinction between volume and mass becomes crucial. You let your thoughts wander through this quiet paradox. UY Scuti, for example, is enormous in size, its radius vast, but its mass is relatively modest among giants, somewhere between 7 and 10 times that of our Sun. Compare that to a star like R136A1, which you will soon meet. That one is far smaller in diameter, but could contain nearly 200 or even 300 solar masses. It blazes with intensity, not through sheer size, but by its unimaginable density and fusion rate. Why is that? You consider the balance at the heart of every star, the push and pull of gravity and pressure. A massive star's gravity pulls everything inward, while fusion at the core pushes outward, releasing radiation. This balance defines the star's shape, size, temperature, and lifespan. The more massive a star is, the greater the pressure at its core To maintain equilibrium, it must fuse elements more rapidly. That intense activity makes it brighter, but it also shortens its life. A giant like R136A1 might burn through its fuel in just a few million years. Meanwhile, a smaller star can shine calmly for tens or even hundreds of billions. Yet not all massive stars are large in radius. Many, like blue giants and Wolf-Rayet stars, are compact and hot. Their outer layers are stripped or compressed. Some, despite burning brightly, are barely 10 times larger than our Sun by radius. Nothing like the sprawling atmosphere of a red hypergiant. It's like comparing a bonfire to a smoldering ember the size of a mountain. Both burn, both glow, but one is intense, short-lived, the other diffuse and slow. This tension shapes every step of a star's life. Mass is also destiny. A star's mass determines what it becomes when it dies. If it begins with under 8 solar masses, it might swell into a red giant, and then settle quietly as a white dwarf, cooling slowly, over trillions of years. But if it starts with over 20 or 30 or more, its end is cataclysmic. A supernova, a neutron star, a black hole. There are thresholds, and you pass them silently as you drift. Somewhere behind you lies the boundary between stars that end quietly and those that collapse with violence. Somewhere ahead lies the limit where even neutron stars can't survive their own mass, and space folds inward. Some scientists propose more exotic ends. Quark stars, for instance. Hypothetical objects denser than neutron stars, but not quite black holes. In these stars, neutrons are squeezed so tightly that their constituent quarks may separate, forming a sea of strange matter. No such object has been confirmed yet, but the physics doesn't rule them out. Somewhere in the deep silence, perhaps one already exists. Back in your current path, mass continues to guide the stars you approach. The next behemoth, Stephenson 218, is an oddity. If estimates hold true, its volume exceeds even UY Scooties, and yet its mass, while substantial, is likely under 40 solar masses. It is wide, but not wildly heavy. A reminder that size does not equal strength. This behemoth likely belongs to a stellar association, a loose group of red supergiants known as Stephenson 2, or ST2, located around 19,000 light-years from Earth. The entire region glows in infrared, partially hidden behind a thick layer of interstellar dust. To see it, astronomers peer through long wavelengths, watching for thermal traces that shine. Like heat seen through fog, you reflect on how much of the universe is invisible, not because it's hidden maliciously, but because your human eyes are tuned to such a narrow band of light. Like listening to a song and hearing only one instrument. Fortunately, your thoughts have no such limits here. You float through X-ray bursts and infrared ribbons, through gravity waves and magnetic storms. Each layer of the universe adds another brushstroke to the vast, silent portrait. And as the shape of Stephenson 218 rises before you, still distant, still only a ghostly glow in the haze, you consider the quiet truth that space teaches best. That scale is not always power, that the universe is not arranged by what impresses the eye, but by what holds its balance. You drift slower now, as if nearing the edge of something sacred. You've learned how stars wear their size and mass like masks, some bright and dense, some vast and fading, and ahead, the deepest mask yet awaits. You approach a veiled red hypergiant, cloaked in interstellar dust, barely visible yet vast beyond measure. You pass through the last of the open void, entering a field of mottled shadows. The light here is soft, not because it isn't present, but because it is scattered and filtered by fine grains of interstellar dust. This is the domain of Stephenson 218, a red hypergiant so immense it defies simple comparison. Its true nature is shrouded, not only in distance but in uncertainty. Even today, it exists in our data more as a probability than a fully resolved object. The veil around it is literal. thick with carbon-rich dust and cool gas, and figurative, in the sense that many of its measurements are inferred from indirect observations. Still, the picture that emerges is staggering. The star lies approximately 19,500 light-years from Earth, in the constellation Scutum, nestled within a massive cluster known as Stephenson 2, a cradle of red supergiants. But Stephenson 218 is not simply one of many. It may be the largest of all, with a radius potentially exceeding 2,100 times that of our Sun. To put that in perspective, if you replaced the Sun with Stephenson 218, its photosphere would reach well past Saturn, and possibly graze the orbit of Uranus. You float slowly towards this diffuse colossus, and even now, you can't clearly define its surface. It is more atmosphere than object, more presence than point. Its outer layers are extremely tenuous, more like a fog than a skin. They drift, ripple, and escape into space. The density is so low, you could pass through the outer half of the star without ever feeling resistance, without even sensing that you were inside something at all. And yet, you drift through its outer envelope, immersed in a slow, churning sea of heated gas. Here, temperatures are relatively cool, around 3,000 Kelvin, and the pressure is low, but deeper in the story changes. The further you go, the more intense the heat, the more violent the motion. Turbulence rises, the fusion furnace stirs. Stephenson 218 is thought to be near the end of its life. Like UI Scuti, it has exhausted the hydrogen in its core and is fusing heavier elements in successive shells. Each fusion layer is like a nesting doll. Hydrogen, helium, carbon, oxygen, each deeper, hotter, and shorter-lived. Eventually, as with all massive stars, it will build up an iron core, and when that happens, gravity will win. In a fraction of a second, the balance will collapse, the core will implode, and the outer layers will rebound in a supernova, an explosion that will send shockwaves through the surrounding dust and gas, igniting new stars in its wake. It is the ultimate punctuation mark to a stellar life, but sometimes something even more exotic occurs. If the collapsing core is massive enough, the pressure can go beyond neutron degeneracy, the point where even neutrons resist compression. Gravity wins entirely, space folds in on itself, and the result is a black hole, an object so dense, not even light can escape. It is the final victory of gravity, the quietest and most complete. You float away from this imagined core, back toward the outer layers. Here the gases are lighter, more diffuse. Solar winds blow steadily outward. In massive stars, these winds are intense, stripping away mass at phenomenal rates. Over millions of years, a star might lose half its mass or more before it ever